Today's session is first revision session for the end sem.
Which weeks will be covering today?
So probably we will try to cover from week 1 to till week 4, or maybe try to.
Sir, start from week 5 onwards. Week 1 to 4 has not much content. We can cover that afterwards.
So the next session is for the onward. Yeah, so that's the today depend on like the next session is will take by this. The next is on 29, I think. The next is on 29, which will taken by Subhajit onward, maybe from 5 to 8.
Yes, sir. You try to cover like the way it is required for
and after next or maybe he will try to cover 6, 7, 5, 6, 7, and next one is there are 4 revision session, I think.
Yes, sir, there are 4 revision sessions, so we would like to know how it is divided so that we can come prepared accordingly.
So like today's session is till 1 to 4 or probably 5. Majorly, like we will try to cover the vector space. That's the main thing there. And
Sir, I want to ask one short question, which I am very doubtful about. Sir, अगर कोई हमें फंक्शन है, हमारे पास एक फंक्शन है and we are given a point, उसकी उस पॉइंट पे लिमिट एग्जिस्ट नहीं करती, तो क्या उसका डायरेक्शनल डेरिवेटिव या पार्शियल डेरिवेटिव एग्जिस्ट करेगा क्या?
लिमिट एग्जिस्ट नहीं करता तो डायरेक्शनल डेरिवेटिव एग्जिस्ट करेगा. 1 मिनट. लिमिट एग्जिस्ट नहीं करता मतलब कंटिन्यू नहीं है, कंटिन्यूअस नहीं है, तो मतलब
डिफरेंशिएबल भी नहीं है.
नहीं, अगर डिफरेंशिएबिलिटी का मतलब यही है कि वो मतलब in all direction you can evaluate the directional derivative. The differentiability means
sorry sir,
मतलब differentiability का मतलब ये होगा कि in any direction you can get the directional derivative. तो अगर उस पॉइंट पे लिमिट एग्जिस्ट नहीं है तो मतलब डायरेक्शनल डेरिवेटिव एग्जिस्ट नहीं करेगा in any direction. हाँ, in any direction.
तो भैया उसका लिमिट एग्जिस्ट करना जरूरी है, राइट सर?
So could you please also share the weightage of the week wise, because in quiz 2 the more stress was given on week 7 and 8, probably less on 5 and 6. So it should not happen कि we prepare for all weeks and then we come to see in the quiz that only last few weeks are coming.
Okay, so as a weightage you can think like
please share the weightage please.
So as a weightage you can think like 50% marks will come from before quiz 2 and 50% will come from after quiz 2. Okay, right, like that. And the all topics are important. Like I have posted in the discourse also one thread.
Could you please repeat what just you said, please?
I just said 50% will be before to quiz 2 and 50% will be from after the quiz 2. Like
so week 1 to 8 50% and week 9 to 11 50%.
50%, like that.
Sir, एक और I want to ask one more question. Sir, in this multivariable calculus, all the fundamentals of one-dimensional or one-variable calculus are applicable, right? For example, if a function is suppose the limit exists and the limit is equal to the function value at that point, then the function is continuous. If the function is continuous, then we have to check for differentiability using the definition. Right, sir? We used to do like this in the one variable calculus. So similar rules apply to this multivariable calculus, right, sir?
Same thing.
Sir, actually, I was not able to get limited maturity from me.
No, you are not audible.
Okay.
Yeah, your voice is very low. So let me tell you the revisions about the revision session. So like today is from week 1 to 4 and then next one is will be covered to 5, 6 or maybe 7. Then next one is 8, 9 and last one maybe 10, 11, like that it will be covered. So you can think like that. Today is still, I will try to cover till week 4 only, and or maybe 5 also. The next one is will take Subhajit will take, and he will cover try to 6 and 7 or 8 also. Then after 9, 10 and 11, like that. How much how much possible to cover in these 4 weeks? We'll try to cover those in the prescribed
Could you
time.
please try to
Sir.
prepone the last session? It was on Friday, just immediate to the exam. Is it possible?
Last session is on not Friday, which is on
Yes, it's on 29.
29. Last session is on 29.
Achha. Before end term also one revision session was there in the calendar.
5th of August.
5th of August, sir.
Okay.
Sir, from week 1 to 4, we have discussed many a times, I guess, and most of the doubts are clear.
Mhm.
So, can we start with week 5? Because we have already covered week 1 to 4 n number of times,
Okay.
like in live sessions.
Okay.
Yes, please.
So if
And
you
the
are
last revision session is on 5th, right? 7th is the exam. So if it's possible to prepone little bit 1 or 2 days, it's really helpful because it's the more weightage.
Yes, sir. Yes, sir.
okay,
If it
so
requires for like 1 to 4 majorly, then we should cover.
Sir, and from week 9, in week 9, the limit and continuity part I was not able to get. So can you help me on that?
okay, this is 3 and 5. Yeah. That's why the revision sessions are. And also one thing you can do, you can also watch the session which is taken by Subhajit also. Me also I have taken. So which is on YouTube, right? So you can watch there also. And yeah, surely if you are here, we will also discuss those. Okay, so
Yeah, I have doubts from week 10, 11. Can I ask at the end? Small doubts only. It will take just few minutes only.
Okay.
And just one request to the entire team, whenever you're revising the concepts, if you take a few problems along with that, that would be better. Because concepts always we can go back and revise. But if you take some problems along with that, that would be better.
Yeah, surely. So today I thought like this. Like I will like when we discuss the concept, I will take some activity questions, which is exactly on depend on that concept, and along with the example, we will discuss.
So we are doing from week 1, right?
Week 1 to 4, try to cover. Yeah, if everyone is agree to from like onward 5, then yeah, there is no issue for me. I will start from
Actually,
Yeah, I
week.
am
vector
agree,
space
sir.
onwards will be better. Week 4 vector space is there. No? From there, if you start it. will
Okay,
be
so
better.
from
Yes, sir.
vector,
Yes, sir.
yeah,
Start from the
let's
vector
start
space.
from
Please
let's
cover week 1 to 4, briefly.
Yes, sir.
Start from the start.
The
Yes,
basics
sir.
are
Yes, sir.
important.
Yeah,
Sir,
so
that
that's
is
the thing.
better.
Yeah, that's the
It would
thing.
be structured, sir, even the lessons and everything. We can speed up if everyone knows the
Yeah,
concept.
from week 1 and 2, we will like very fast we will do, and week 3, like which is in the
Yes.
vector space, we will spend more
Yes,
time
sir.
on there.
Yes, sir.
Yes, sir.
So we can do like this.
Yes, sir. Yes, sir. Agreed, sir.
So in week 1, we know about the vectors and matrices, system of linear equation, and determinant. And determinants are 3 videos of determinants, part 1, part 2. So first thing is, what is vectors? So in that, like sir, it says just if you think like columns, if you write the entries in column wise or in row wise, that's all. These are called the vectors. But the vectors have some specific, like saying to be vectors in the vector space is different, and talking about in writing in the like this is different. So writing the vectors in a matrix, okay. I mean, difference means to say when the definition come from vector space, then there are 8 properties, like that set should satisfy some 8 properties. If set satisfies those, those property, then the elements of those that set is called vectors. So probably the thing is, we in this course we majorly studying this R2, R3. So R2, R3, Rn. So element of these uh, this vector space, actually if you write like this, like if you take the one element from R2, you will write like this. Used to write like this, or maybe in matrix form if you write, it will write, we used to write like this. So that's why generally in the video, if in the first video you see that, so that's why I started with the saying to be the vectors will be a column of a list or maybe a row of a list, like that. Sorry, so the reason behind this, what is the why we are saying why sir is said like this, the reason behind this, because the R2, R3 are in this course we are majorly studying the vector space R2, R3, Rn till Rn. So the element of these vector spaces are listed like this. If you want to list like this, this is from R4, or if you in matrix form, if you write like this, so in the row wise like this, or maybe in column wise if you want to write, then it will be like this. So this is the one list of, if you give a name to each entries, like this is 1 kg dal, 1 kg rice, 1 kg like this. So this is one list, and list of collection of list, take the one column, this will represent a vector, saying to be represent a vector. So reason behind this saying to be the this one, these are the vector spaces. So that's all this is about for the first video. This is saying to be the vector space. Like what is vectors? So vectors is the definition from onward, from week 3, saying to be the elements of these are in the list of, in the kind of list, is one that's called vectors for the first video. Now the next one is about the matrices. So matrix is most important part of the linear algebra for this course. If you studied, you already studied the linear transformation, and uh, whatever the vector spaces come, and whatever the vector space you have seen, there are some vector spaces. Apart from these vector spaces, there are some vector spaces writing to be like this, var. So this is one kind of collection of matrices. This represent the collection of all like collection of matrices of order 2 cross 2. Whatever the entries will be there, it will be the collection of scalar matrices or symmetric matrices. So there are some types of matrices. The first type is, you can say, like if, so what is matrix? Hope you know that writing the like writing the numbers in the array kind of. If you arrange some entries, like if you write like this, then just saying to be this is a collection, or this is the range, or this is the array of number. So, and how many entries you are giving, just name those, like how many rows are there. If you count those, these are the rows called the rows, and these are the called columns. So whatever you will say here, this is of 2 cross 2 or 3 cross 3. The number of rows tells here, and number of columns tells this one. This much columns are in this matrix, and this much rows, or this many rows in this matrix. So there are some specific matrices like symmetric matrices. So symmetric matrices is one of the important, like not important means saying to be, it entries are, if you write like for example, if you suppose this is a matrix of order 3 cross 3, suppose the first entry is A, B, C. So when you write this the next one, so before to symmetric, there is one concept, transpose of a matrix. So transpose of a matrix is writing, suppose this is a matrix A, B, C, D. So these are the rows. If you write these rows in column wise, just column A, B, and C, D. This row is converted to this in this column fashion, and this row converted to in this column fashion. So if you this matrix, now whatever you formed after writing these rows in the column wise, this is called the transpose of this one is called the transpose of this one. This is transpose you are doing. Transpose is one kind of a, if you think transpose is one kind of a linear transformation also. This is one kind of function. If you want to define it like this, in the like now you have studied the whole linear transformation, so I can tell you like in the terms of linear transformation, in terms of mapping, in terms of anything, I can tell you. So converting a matrix in a different, like getting a transpose of a matrix is like a function. So the function will be, if you want to define it, it can be from 2 cross 2. You are collecting the matrices of order 2 cross 2 to 2 cross 2, and you are defining like this a transpose. So this is actually a linear transformation from this vector space. This is a collection of matrices. This forms a vector space with some specific operations, and operations are usual addition and scalar multiplication as you used to do in matrix. That's why this forms a vector space, and this map is, like I'm saying, to be your transforming this matrix to in this fashion, you are getting the transpose of the matrix. So so transpose of matrix. So when you studied, like you know that this is the transpose of matrix. So there are specific matrices regarding to this transpose: symmetric matrices, or symmetric matrices, antisymmetric, diagonal. So these two are the main thing for regarding to the transpose, and I'm just naming it here. And antisymmetric. The third word is diagonal. There are, I have seen in many times, like diagonal and scalar. There are some many doubts in like which matrix is called diagonal matrix and which matrix is called scalar matrix. So the naming to the scalar matrix is there is a region, and naming to be a diagonal matrix also a region. Why you call a matrix, if this matrix is one kind of like k k k, and rest entries are the entries at the diagonal will be a particular real number, and rest all r will be the diagonal is particular real, rest all are 0. So this is called the scalar matrix. The reason is, if you multiply this matrix with another matrix, so it will be have like you are multiplying. It will be have like a scalar multiplication. So that this scalar matrix can be converted in the k time identity matrix, and now multiply, you will get the same matrix. So this k time the same matrix, and now it is behaving like a, you are multiplying this scalar k. Scalars are nothing but the real number. In this vector space, we are just calling it as a scalar. Otherwise, there is no difference. Scalars are real number, and real number, why this is a different name, there is one region. Actually, in vector space, we have seen the term field, the field word, and in this course only we are studying on the field r, and the r means just saying to be the real number. So field is the term came from this when you study in the pure mathematics, group theory, ring theory. Then next one is used to come field. And field, why it is called the field, reason is you can do anything, like you are in a ground, you can on a playground. So anything you can do in that playground, in that playground. So field, saying to be field means, if this is called a field, the reason you can whatever you want to do in this, like this r, this is the r. So whatever you are want to do this in this set, like multiplying any to real number, adding to real number, anything, any operation you can freely do. That's freely you can do freely. That's why it is called field also. when you study the pure math, then you will know what the mean of field. But here here the field means just know that real number, that's all. No need to know anything more for this course. So elements of this real number, just you can call it as a scalar.
Sir,
Hmm.
hello.
Hello.
Sir, can we say that a scalar matrix is always a diagonal matrix, but a diagonal matrix can't be a scalar matrix?
So yes, so scalar matrices are, you can say these are the scalar matrices are diagonal matrix, but diagonal matrix cannot be all diagonal matrix cannot be scalar matrix. There are some matrices different from like, so yeah, diagonal matrix is the diagonal entries will be non-zero. It can be zero also, not all, but at least one, or maybe there are many like I have seen in the discourse also, zero matrix, if you want to say zero matrix. So you can call it as a scalar also. You can call it as a diagonal also. Okay. This is also symmetric matrix. The reason is not we are fixing like diagonal entries or exactly non-zero. There are some possibility there. The diagonal entries can may or may not be zero also. Like here is zero, then it may be a non-zero, b non-zero, and rest all r can be zero. So diagonal matrix is not exactly as you can see for a with respect to this scalar, you can see all are k, but here it can be different real number. That matrix is called diagonal matrix.
Thank you.
And this is all about the diagonal, scalar, symmetric. The next one is.
Hello, sir.
For
antisymmetric matrix, diagonal are 0.
For antisymmetric, diagonal should be 0. Yes.
Okay.
One second. I'm sorry. Scalar and diagonal, how do they differ? Scalar is also a diagonal, right?
Scalar is also a diagonal matrix. But diagonal matrix may not be scalar matrix.
Because diagonal has all the numbers the same, or
no, diagonals may have different, but the scalar
diagonal may have different. Okay.
But scalar have the same entries and at the diagonal.
Okay.
Sir, why antisymmetric matrix?
Diagonal. You can directly infer that, right? Like reason is antisymmetric means suppose A, B, C, and B, let's say D, E, and C, F, C something maybe. Suppose this is a if you are saying this matrix is antisymmetric, means if you do the transpose of it, so it will be the same. Just you will do the minus time. What do you mean by antisymmetric is minus A. This is the mean. If you take the transpose of it, it will equal to the minus of the same matrix. So if you add these, if you see that only 0 can sustain on the when you do the minus of each entry. But the rest all cannot sustain at
And so for symmetric, it is A transpose equals to A.
For the symmetric, this is for antisymmetric, and for symmetric, A transpose should be A.
Okay, thank you, sir.
So 0, the reason is for why diagonals are 0 in the antisymmetric, because of 0. 0 can, if you do minus of it 0, still it will be 0. So that's why if you do the minus of each entry, the 0 can sustain only at the entry. Otherwise, if you non-zero entry will do, it will different from this one. So that's the reason. And the next one is now next is the
antisymmetric. You can say
Can you repeat that, sir?
A12 is equals to A12 is equals to A minus 21.
Actually, yeah, it is in the mathematical way. If you will write like a writing to be A matrix is, you can write like this: Aij. This is the saying to be Aij. This is the matrix.
Correct.
Now you can do. You are saying this A transpose is minus A. That means if you take it here, So if you take the transpose of it, it will be, we have like A, J, I. Now both are same means A, I, J equal to minus J, I. And if you solve this, and so now if you solve for the, if you solve this equation for the diagonal, so AI diagonal means Aij means the entries of diagonal is I kind of going to be both are the same. I equal to J in the diagonal at the diagonal. So that's why AII. So AII equal. So if you compare these two equations, that means you are getting at diagonal minus AII equal to AII.
So why we put minus?
Because of antisymmetric, na, you are saying A transpose of A is minus A. You are doing the each entry, you are putting ahead minus at the each entry, and we are taking the transpose up, and you are getting A transpose equal to minus A. That's why the reason.
Okay, if we put minus and do the transpose, then we can see that it's it's symmetric or antisymmetric.
If you are putting minus to A, so that is saying to be the antisymmetric. And if there is no minus, when you are taking the transpose of that matrix, you are not getting the minus here. That means this is the symmetric. This is for symmetric. For antisymmetric, it will behave like this.
After interchange columns, we put minus, no?
After taking the transport, put minus there. And if in that case, minus say that you are whatever you are getting, in that case minus is equal to like putting the minus in front of each, and whatever you are transpose you are taking, if both are same, then you will say this matrix is antisymmetric.
I'm saying in general, if in the matrix, if we do interchange a column, then we put minus sign. You think so?
Like, can you take a small example, sir?
For example, you can see that, like, let me give you an example. Like, this is 0,
0, 5, minus 5,
0, 5, minus 5, and 0.
0.
See, if you have this matrix, okay, let's say this is a matrix A. Now, if you take transpose of it, what you will get?
0 minus 5, 5.
0 minus 5,
5,
0. Okay, you are getting this transpose. So is there any relation in these two?
No.
There is one relation that if you write minus A, which is 0 minus 5, 5, 0, which is exactly this one, this A transpose. See that this is the A transpose, right?
Yes, sir.
So that's the mean here. You are taking the transpose of, when you are taking the transpose of this matrix, you are getting minus A. Exactly the minus as here is happening.
So in this matrix, if you perform a row or column operation, when we interchange some column, we put minus sign?
No, so that is the different thing. Whatever you are doing operation is, it doesn't matter it is antisymmetric or symmetric. There is
in general, I'm asking, means if I interchange a column of any matrix, do I put minus sign? So that thing?
No, why you are interchanging row? This is just a definition that you are changing the each row in the column wise. That's all.
Right.
There is no you are not interchanging rows or column. You are this row can be transformed.
Transpose I understood, but I was thinking that when we do this column and row operation, there we have this.
Doing column or row operation is totally different from this definition. Different from this definition. There is no relation in antisymmetric and doing the operation in the row or on the row.
This example was symmetric.
This is for antisymmetric. And for example, if you take 1, 5, and 5 and 2, so suppose you have this matrix. If you take transpose of it, so what it will be? 1, 5, and 1, 5, and 5, 2. See that when you are taking transpose, it is exactly equal to it. So this is called for symmetric matrix. You can see the differences for these two. And yeah, I
sir.
substituted here. I substituted here entries at diagonal is 0, because the reason is when you are taking the transpose of it, 0 can only sustain. 0 can manage the minus and plus sign. Otherwise, no non-zero real number can manage the minus plus sign.
So to find whether a matrix is symmetric or antisymmetric, we will have to find the value of the determinant. Then only we will be able to find
No,
it.
there is no relation with the determinant.
So value of, so how would we know without seeing the matrix?
So it should be written there, this matrix is symmetric or not. It should be written there. No? How you will know that this I'm saying this matrix is, let's say I just said this is a matrix. How you will tell that this matrix is symmetric, not symmetric? I will write here, okay,
Work
this
out their
matrix.
values, right?
Huh?
We'll work out their values, right?
If B is written like this, some entries are written, then what you will do, you will take the transpose of it, okay? When you did the transpose of, if you write the column in this rows in column wise, and now you will compare that, okay, we are getting the exact B or minus B you are getting, then you will tell that, okay, this matrix is going to be symmetric or antisymmetric.
If the diagonal are not 0, that time it will be sustained antisymmetric.
The simply thing is, if
Because
diagonals are non-zero, then
taking
that can be never be antisymmetric. Directly you can say. If suppose somebody says B is a matrix and said that diagonals are non-zero, this is the question. He just gave the information that B is a matrix where the diagonals are non-zero. Then you can directly say this matrix is never be antisymmetric. Never be.
No, sir, antisymmetry means a transpose equals to minus a. When you are taking a, when you are given a, if diagonal not 0, then we can transpose. It will be give minus a sometime.
Yes.
Let's example, they are given one antisymmetry matrix, but diagonal not 0. Not antisymmetry matrix, one matrix which diagonal not 0. When you are take transpose, then we are get minus.
Okay, so now next let's move to the next. There is not no need to spend more time on antisymmetric and symmetric. This is just a definition and just telling to be the transpose of matrix. If you will take your time, you will easily understand what is. If you are getting confusion, just spend time, you will get there. There is not a deep understanding like vector space, a deep concept. This is just a visualization how the entries are behaving. That's all. And the next one is system of linear equation. Before that, when you studied the matrix, there is one term associated with this matrix is called determinant of a matrix. And this is one kind of like you are. This is also, if you think it as a function. This is also we have like a function. How I am defining a function? If you think like I am defining a function t, let's say t from m2 cross 2 over r. So the for the term determinant associated with the matrices, there is one condition that matrix should be square matrix. Otherwise, you will never you are unable, like there is no definition for evaluating the diagonal that is called rectangular matrix. There is no definition for the rectangular matrix. The definition is for the determinant. The word associated, the determinant word associated with matrix for only the square matrix. It can be different order. It can be of order 1 cross 1. It can be order of 2 cross 2 or 3 cross 3. Means number of diagonal, number of rows should be equal to number of columns. In that case only you are able to evaluate the determinant of a matrix. So I just said that you can associate a map from the determinant word. So this mapping will be from M2 cross 2. This is the collection of matrices of order 2 cross 2. This is going to be the collection of square matrices. And now I am defining this. Suppose A is a matrix from this collection of this matrix. Collection of matrices. This collection A is a matrix from this set, you can say. And this is defined like determinant of it. So determinant is you can think as a function from this set. I'm just giving a view only. There is no mean to say anything. I just giving, you can think as like, you can think there are some function you can define like this. I am giving a function which is you used to see from only R2 to R or from R to R. But I am just giving to the some view from not only R, there are different sets regarding to the different segments from the collection of matrices. So you can define a mapping this one. So as previous one, I just said when you are defining a map from A to A transpose kind of thing. So in this case, this map is linear, but for this case where you are defining this map, TA is equal to determinant, this map is not linear. That's the mean I want to say. If you done with the linear transformation already you did. So linear mapping is what do you mean by linear mapping is only if the mapping is behaving like this. And another thing is P of Cx is equal to this one. These two property, if any map, not only saying to be from the vector space to vector space, if just in the general case, if a map is behaving like this, that map is called linear map. So this transpose is actually work as a linear map, but for the determinant is one will not work as a linear map. The reason is you know that determinant of A plus B for two matrices will never means may not equal to determinant of A plus determinant of B. But if you see for the transpose case, you are taking
It's
the
not equal to, right?
Sorry, it may not equal to, sorry. For the transpose case, you know that if you are taking the addition of two matrices and take the transpose, it will be the same as saying to be this one.
When you say transpose, do you mean transformation or which one?
Transpose means transpose means here transpose of matrix, and this T is I am saying just saying to be the map.
Okay.
Oh, so there are missing so many things. For the transpose I am making here a small t. This means transpose of a small t. So this map is linear, but this map is not linear. This is if you are for this case, for the determinant case. Just for the I am just saying for the just a way, like saying to be knowing to be the mapping only, that there is nothing. There is no mean to saying or there is no relation with the quiz I am saying. It's just an information I am saying. Because now you know the linear map, linear mapping, linear transformation. I am just collecting those information which you have already did. That's all. Now, determinant word I said, yes.
So is that sorry, A transpose plus B transpose?
A transpose, this is plus here.
Okay, thank you, sir.
So,
small question on determinants.
Sir, here A plus B transpose is equal to A transpose plus B transpose.
B transpose, yes.
So I have a small question on determinant.
Yes.
If A is 3 by 3 matrix with non-zero determinant, and if determinant of 2A is equal to K times determinant of A, then what is the value of K?
Sorry, if you have determinant of A equal to some, you are saying some real number. Okay, you are giving some real, let's say alpha. So what is going to be the determinant of 2A, right? Is this question?
So we have to find the value of K. Determinant of 2A is equal to K times determinant of A.
K times determinant of A, okay.
What is the value of A?
So we don't know about is this 3 cross 3 matrix?
So the reason is here you should there is order is needed. It will be surely in the question. It will classified that okay, order of this matrix is going to be, let's say, n cross n. Any general case I am saying order of this matrix A is n cross n. So in that case, your K is going to be what is the relation?
2 power n.
2 power n.
2 power n. Yes.
This one. This K is going to be 2 power n. The simple region, no need to remember this. Just a simple region I'm saying, no need to always remember. If you have a matrix, let's say I'm just giving to order 2 cross 2. If you have a matrix A, B, C, D, general matrix, if you and let's say determinant of this, let's say this is A, and determinant of A is, let's say, alpha, I'm saying. You got able to, or that is, if you evaluate the determinant, it is going to be AD minus BC. This is going to be determinant of A. Now determinant of, let's say I'm multiplying 2A. So what do you mean by 2A means? Multiply each entry with 2. 2B, 2C, 2D. Now, if you take the determinant of it, so there is now the term came, simple thing is, using this one, I will back to this. There are some, like, as you know, the definition for evaluating the determinant of order 2 cross 2 is A, B, C, D. This is a method. This is an algorithm. The determinant of this matrix is AD. If you multiply these to cross multiplication minus BC. This is the for 2 cross 2, any general. This is for general case. For order 3 cross 3, suppose this is A, B, C, D, E, F, G, H, I. Suppose this is the matrix of order 3 cross 3. So what you will do? You will take the first entry, this one, and neglect these two, row and column, respected row and column, and you will get a matrix here, okay, which is E, F, H, I, and determinant of this is means A time determinant of a smaller one. This is an algorithm. Hope you know that in the video. I am not going to tell that. This is an algorithm. All of you know that what is. I want to make more specific on the property when you are doing, when you are interchanging rows, or maybe you are that is elementary operation. That is called elementary operation.
Yes,
So
sir,
I
but in
hope.
my question, the A was 3 by 3 matrix.
If A is for 3 by 3 matrix, so that means just change n with 3. So K is going to be 3 here.
Okay.
2 power 3.
Okay, 7.
So I will tell the region also. I will back to this one. If you evaluate directly, direct method, you will get the same thing. But I want to tell in the terms of elementary row operation. So there, if there is one, there are 3 types of elementary operations. In the 3 cross 3, I am telling it will apply to any order n cross n. It will apply the same for any order of matrix. So suppose if you have matrix A, B, C, D, E, F, G, H, I. Suppose if you have matrix this, so the first type is called interchanging. If you, I'm just naming it. You can call different thing. For this time, I'm naming it. The first type is I'm interchanging 2 rows. Interchanging 2 rows means any 2 rows, not only these two. You can change any 2 rows, this one and this one. If you are interchanging means A, B, C, G, H, I, and D, E, F. So I did an operation. What is interchanged? R2 and R3. This is the notation in the mathematical notation, if you want to say. So I interchange R2 and R3. So what is going to be now when you interchange this? You got a different matrix. But suppose this is a matrix A. After interchanging 2 rows, you got matrix B. So there is one relation in the determinant of these 2 matrices. What is the relation? If you, let's say, determinant of this matrix is determinant, I am just denoting it A, and this is determinant of matrix is det B. So there is one relation that determinant of this B is exactly equal to
minus determinant of
A. This is one relation. When you obtain another matrix after interchanging, these 2 matrices are different, entries are different, but there is a relation in the determinant, which is this one. And you can confirm with the doing an example. This is a simple thing. Doing an example will take time because that's come for the numerical link. I'm not so good in numerical, so for me it will be difficult, but you can check yourself. The another type is
because of the minus sign we use in between, no, sir. For the odd rows, odd cofactors, we use negative.
Yes,
So
yeah,
when
and
we interchange
the
them,
reason, yes, correct. The reason behind it is also based on this algorithm. What I'm writing, I just said there is an algorithm. All of you know that how to evaluate. So the reason behind this is this algorithm itself tells you that why this is going to be minus. It's up to you. You can check. It will take time, but you can do yourself because of this minor and cofactor term. I hope all of you know that. I'm just leaving the adjoint word. Yeah, I just skipping the adjoint word. I'm mainly this matrix. I want to come this types of matrix because there are some questions which is just saying to be okay. The questions may be like this. I got suppose A is a matrix and I got a matrix. I obtained a matrix B. How I obtained? I obtained like I multiplied row 1 of A with 3 and added in row 2. I added in row 2. So what it means that this is one another type.
Let us take a question of practice assignment 1. It will resolve this. Question number 6.
So there are some question. It will not. The question will be like the entries will also not given to this of this matrix, but only the some terms are written there that we obtain matrix B from A. How we obtain? Take the row 1 of matrix A, multiply with 3 and add into row 2. So whatever you will get the matrix, that is I am saying matrix B. So and said that okay, determinant of matrix A is 5. So what is going to be the determinant of B? So this is that's why let me tell you the type now. This type of question can be created. So type 2 is if you have a matrix as here, I am taking the same matrix here, this one, A, B, C, D, E, F. If you multiply any row, not any row with a real number, let's say alpha, I am multiplying here, any row, only a single, like as you know the scalar matrix with the, scalar multiplication with the matrix is, means you are multiplying each entry with 2. But here is, so no need to confuse here. What we are doing, we obtain a matrix B here. What is B? B is alpha time A, alpha time B, alpha time C. I just multiplied a real number, let's say alpha, with a particular row, and rest all are the same, like A, B, C, D, E, F, G, H. So see, I obtained this matrix B from A. What I did here, I multiplied a row. First row I multiplied with the scalar, any real number, let's say alpha. Now, whatever you obtained matrix B, there is one relation. See, these two are different matrices. A and B are different matrices, but there is a relation in determinant. That relation is actually determinant of you. When you evaluate the determinant of matrix B, it will be exactly equal to alpha times determinant of. This is the another relation when you obtain the matrix from the previous one. This is I'm just naming it. So what I'm doing here, see that I am doing a elementary operations, elementary row operation. Row operation means I am doing according to the rows. I am multiplying a alpha in a row only, particular row. What I did here, I interchanged two rows. And so that's the meaning to say means I am doing some elementary row operation in this matrix.
So just a quick question on this. For example, when we have multiplied it with one row, if we multiply the entire matrix, all the 3 rows by alpha, then it will become alpha into alpha 3 times, right?
Alpha into alpha 3 times.
Okay, so it would be like if I multiply alpha value, take alpha value as 3, if I multiply all the rows by 3, it will become 27 determinant of A, right?
Yes. That's the meaning. That's why I just now I just coming to hear this, going to tell you the multiplying a scalar with a matrix is how the affecting determinant, why you are getting like this 2 power n. The reason is when you multiplied a scalar with a matrix, means you are multiplying each entry with 2. Now see, this is, if you say that this is another matrix, I want to evaluate the determinant of this matrix. So determinant of B means, now if you see now compare with the previous one, matrix A, you will see that okay, this one is going to be the same with the multiplied 2. This one is the same entries but multiplied with 2. So what you will do, what you will say, 2 time this one, 2 time means 2 time and the determinant of A. So 2 square determinant of A. So determinant of this matrix is, here if you concern with the order, so whatever the order for the square matrix, whatever the going to be the order is, will come to as a power of the scalar, of that scalar. So the reason is this property, this one comes from the type 2 operation. I'm just naming it type 2. It's up to you, whatever the type 1, you can call it type 1 itself, this one. I'm just making an order, type 1, type 2. Now the next operation is, so this one, this is be careful with the this one and this one. A scalar matrix with a scalar multiplication with a matrix is multiplying each row, each entries with 2. But here is totally different thing. We are comparing the determinant. So there is one thing that multiplied a row with a scalar. It can be like, let's say this is beta, this is beta, this is beta, this is gamma, this is gamma, this is gamma. So in that case, what is going to be the determinant of this matrix is just alpha time beta time gamma time determinant of it. That's it. Now the type 3 is saying to be the same matrix you have.
Hello, sir. If we do it for column also, will be like same thing, right? Like alpha A, alpha D, alpha G, and beta B, beta E, beta H, like that.
Yeah,
Column
actually it is the same, but there is one region. The reason is
determinant of
A exactly equal to the determinant of A transpose. Because of this reason, you are able to the all things as according to the column, whatever here is happening. That's all. So because of this property, determinant of X is exactly equal to determinant of A transpose. That's why the elementary row operation is sometime is called for this course we are doing only for elementary row operation. But when you come to in pure math, so there is another term came for elementary column operation also. As here you are saying, you are multiplying the column with a particular real number. But these two operations are totally different. That's why for this course we are specifying, or not we are, means this course is specified for only doing row operation. For the general case, these two operations are totally different and affect differently to a matrix. When you come to the pure maths, I'm saying. For the general case, doing here for the matrix, for simple matrix, it's look like very same, but these two are totally different operations, row operations and column operation, and affect differently also. It defect differently also. The reason is when you there is one when you do pure math, there is one doing the finding the inverse with some different. Actually, it's come in the numerical analysis. When you do, that's why I'm saying when you do the mathematics course, you will many things you will do. You will learn their numerical analysis. There is one algorithm based on this elementary row and column operation to finding the inverse of matrix. Something is there in numerical analysis. So
is there any difference between A transpose and A in bracket then transpose?
A transpose
and
and
A in bracket.
Okay, you are
Then
in transpose.
Yes.
No, so it will clearly mention that it will be again you are like whatever you are doing here. It mentions it like you are. This is the same thing now. A transpose here or A transpose, you are writing the same thing. It will now the next bracket will decide what you are doing.
Okay. Right. Thank you.
Now the type 3 is adding a row. Now I am getting a matrix B, which is something different. This is A, B, C. What I am doing here? D plus I am multiplying the third row with alpha. Let's say this is let's say here I am alpha G H sorry E plus alpha H F plus alpha I. These are the A, B, C, and rest is G, H, I. So I got a matrix with this kind of. And if you see the entries here, what is happening? I multiply this matrix B I obtained. I multiplied the third row with alpha and added to the second row. So for this can be in general case and many times. It can be many times. Like what I am doing many times means I can obtain a matrix C like this. What I am doing here, A plus beta time D E D alpha G plus B sorry not plus B plus beta time E plus alpha H C plus beta time F plus alpha I, and this is the same. Or if you want to say it's the same as previous one, D E F G H I. So see that what is happening here, you are obtaining a matrix C, which is what is first thing is the entries are like this. So in that case it will be the thing like what I mean to say, the determinant of this matrix C will be exactly equal to determinant of A. This one also exactly equal to determinant of both will be the same. Like whatever now, if you evaluate the determinant of B, forget about this one. If you evaluate the determinant of B, it will be exactly the determinant of A. And if you see this operation, this matrix C, you got doing the more many times. So many times this the same operation, but still it will not affect the determinant of the matrix. So mean to say determinant of C will be exactly equal to determinant of the previous one from where you are getting the matrix. So how many times if you want to do, you can do, but it will not affect on the determinant.
So I can say determinant of AB inverse is 1 in this case.
Determinant of AB inverse. So determinant of AB inverse
is 1.
Is going to be 1. Because determinant of, there is some property, determinant of two matrices is exactly equal to saying to be determinant of A into determinant of B. Now as you are getting the determinant of B is determinant of A, you can you can open this bracket. So this is going to determinant of A into determinant of B inverse. Okay, this one, and this is going to be determinant of A into determinant of B inverse is determinant of 1 by B. This is one in another relation. You can search there are many properties. This will never true for general case. Determinant A plus B not equal to determinant of A plus determinant of B. This is never going to be the same for any general matrix A and B, I am saying. But these two properties hold for any general matrix. And now,
so even if we don't know this property, determinant of A, B inverse is equals to 1 upon determinant of B, you can say this AB inverse is identity matrix because A is equals to A, B is equals to A inverse.
B equal to A inverse. Yeah. So yeah, now here is going to be 1 upon determinant of B, and determinant of B is exactly equal to determinant of this one. Is for this case we are doing. And final thing is going to be.
So can we say that in short, after applying elementary row operations, the determinant of any matrix doesn't change; it will remain same. Am I right?
Doing the elementary row operation.
Third type of elementary row.
Or only the third type is not affecting. Otherwise, you can see the effect, right? There are different effects.
Type 3.
For the type 3, there is no effect.
Right.
So this is all about.
So for matrix C, the second row has to be equal to the second row of B, right? Before we can apply the elementary operation on row 1 of C.
No, I just said that we obtain a C matrix C with this kind of. I am not evaluating this. I am not getting this C from B. I am trying to say that I got C from directly A. But the thing is,
what is the operation applied?
The operation is, see, this is the same thing is saying. What is here operation? We added here. If you see that, you can open this bracket. What is happening here? A plus beta D plus alpha beta G.
Yes, sir.
This is going to be. So this is the saying to be the same, like you multiply. See, you added the second and third row with some multiplication, multiplying with some scalar, and then added to the first row.
So we can use 2 rows at once.
So yeah, so that's the mean to say, like only one thing. That's why I'm saying how many times if you want to do, you can do this, but it will not going to affect on the determinant. Like here is just directly we jumped, because here doing the same thing, but one by one. Actually, we got C from first B and then C, but I just said I got C from directly A with this kind of, but it's telling you, okay, first you got B and then C, and determinant of B is exactly equal to A, and determinant of B is exactly equal to C. That's why determinant of A and C are going to be the same.
Okay,
or maybe if you open the bracket, you can see that. Without opening also, you can, using this BC, you can tell. Otherwise, if you open the bracket, you can see that how it's happening.
Okay, got it, sir.
Okay, so this is all about the determinant. And suppose in some question, I'm just giving a trick. Suppose if you there are some question saying to be on the property of determinant. So the simple thing is, the determinant is for the determinant of a matrix for any order n cross n. So see, you can check very quickly on 2 cross 2, and it will apply to the whole n cross n till n cross n. So suppose if you have a question on the property of a determinant, so you can eliminate that option, or you can choose that option, just giving some example of order 2 cross. Taking an example of order 2 cross 2, you can eliminate, or you can.
Could you please repeat that again?
What I meant to say, I'm saying, if suppose there is a option on the property of determinant, and if you want to eliminate, you don't know that property, you want to eliminate, or you want to choose that option as a selector, you don't want to select that, eliminate, you want to eliminate that option. So you can apply that property on 2 cross 2, and if your property is following for this matrix, then you can say that, okay, this option is going to be true or not, according to that, if it is applying for the 2 cross 2. because I mean to say you can, for the bigger case, you can make in a smaller case, or not only 2 cross 2, sometime 1 cross 1, you can check for 1 cross 1 also. But it may not also, 1 cross 1 is directly just doing the real thing. So it will use to see that. But for 2 cross 2, you can use 2 cross 2 and you can choose or eliminate on if that property is satisfied with the particular matrix for 2 cross 2.
Sir, you meant to say when you are given n cross n matrix, then we can check by reducing by 2 by 2 matrix.
So I meant to say, okay, I maybe I moved what I use it. Suppose you want to check that a plus b is determinant of a, or is this is true or not. So see, you can choose a equal to some 2 cross 2 matrix. Here is order is not mentioned here. So you can choose a is 2 cross 2, b is 2 cross 2, and give some real entries and evaluate one by one. See, you can do these things very quickly, and then after add a and b and whatever you got 2 cross 2, and then you evaluate
for
the
in general.
But for this general case, you can do for the specific matrices, and then you can say it is going to be true or not. That's the main I want to say.
So this is irrespective of any scalar or diagonal or zero matrix or non-zero matrix, no?
For the diagonal, it may be. For diagonal, it may be. No, it may not. No, for diagonal also it is not true. Okay. You can check that.
Sir, could you give an example of what you're? I really don't get what we're doing.
This is, I just given the trick that if you want to choose an option, like if
I
you
think
have a test statement.
In practice assignment, that type of question are there in practice assignment. I don't know which week.
If you have an so let me tell
Generally,
you.
Sir, determinant of a plus b is not equal to determinant of a plus determinant of b, right?
If you know that, somebody suppose he don't know that, so
okay,
you know that okay, this is never going to be. Somebody suppose you forgot in the exam, so but still you can do with the giving some example to a, and like you can assume a equal to this matrix b, and then you can check. That's the mean I want to.
Okay.
For type 3, only one row should be changed, sir? Or any operations on any number of rows?
Any operation, and sorry, I didn't get. Can you repeat again, please?
Sir, so for C and B here in the matrix, for C you only change the first row, for B you only change the second row. So the transformation, if we do the transformation for any number of rows, we get the determinant as same, or only one row if we change.
No,
we get
so it's actually depend on, like, there can be like this also, like what I am doing here. It can be like this. Okay, what is here? G plus beta time A, H plus beta time B, and I plus beta time C. If your B is also this one, see that I did these two things, but still it will be the same determinant as determinant of A.
Okay, sir. Clear.
Right? Got it? So this is all about the determinant. I want to tell this property. And next one is very simple thing, system of linear equation. Many times you did that. System of linear equation. So, like, suppose if you, I just in one word, if I will tell that there are 3 ways, like finding the inverse of matrix. Okay, remain to say what is system of linear equation. We can just quickly recall that there are different type of notation writing to be the system of linear equation. Is this tells that A is a matrix, a matrix A. It can be rectangular also, A cross B, and this is going to be the column, some order, whatever you order you want to give. This is going to be a column matrix. This is going to be a rectangular matrix. A tells you the variable. X means here x1, x2, how many variables you are using. It's depend on that. So different notations are there. This is called the matrix form of the linear transformation. Or there are like writing to with the ax plus by plus cz equal to d. Then after, or maybe more general case, a1 x plus b1 x1 x2 plus c1 x3 equal to d1. And then after, see this, the single variable, this single equation is also you can tell it as a system of linear equation. The system of linear equation can be the collection of more equations. It can be single one also, or it can be 2, 3. It's depend on. It can contain more variables, not only 3. It can 4, or it can like if your system this one, this ax is equal to b. You see that this is a single equation with a single variable, but still you can call it as a system of linear equation. So it's totally depend on like a linear equation. Here the word linear emphasis word is that variables, whatever the variables you are using, this should have degree 1. Then you will call it as a linear. Otherwise, suppose some variable contains degree 2, in that case it is not a linear equation. It is a quadratic equation. So, but for this course, for this system of linear equation, we are system that's the word we are using here. Not uses here linear word. Linear means variables contain only degree 1. In that case only we will say the linear. That's why the linear word uses here. And for this course, we are dealing with the system of linear equation, means it can contain the more equations, but each variable have degree 1. So this is if you write this system of linear equation which contains 3 variables and only 1 equation. So if you write this in the matrix form, it will look like a1 b1 c1. Is it correct? x1 x2 x3 equal to, no, I think I'm making
Sir,
wrong.
A1, B1,
Correct.
C1 in
It is going to be like this.
row form.
A1, row form. Sorry, I am just missing here. A1, B1, C1. So this
And
is,
column
and this is column.
Column
It is going to be column. And now this is going to be. So this is the matrix representation of this system of linear equation. The reason is you no need to confuse more time. Like suppose somebody says this is the matrix representation of this system of linear equation, you can confirm with the multiplying. Just multiply that, and if you are getting the same equation, then okay, you can call it as a, yeah, this is correct way of writing the in the matrix form. Otherwise, just cancel it. It is not the matrix form of this system of linear equation. So suppose somebody says that this is the matrix representation, matrix form of this linear equation, just multiply and check that. That's all. You can directly multiply. You know that how to multiply two matrices for any rectangular matrices. I'm saying.
So when do we come to know that the system of linear equation has unique solution or many solution or no solution?
So yeah. So that's the thing is remain. So yeah. So there are now you know that what is I mean to say system of linear equation. So to find the solution of a system of linear equation means linear equation, solution of system of linear equation. You can find the solution of system of linear equation by 3 ways in this course have sir have told. First way is using Kramer. The second one is using inverse, and the third one is Gauss. Gauss is the god for the system of linear equation. Whenever you have system of linear equation, no need to go with this kind of this is specific kind of. Just do using the Gauss. In the question itself, if it is, then you need to go. Otherwise, no need to go with these two. Go with the Gauss. Gauss is actually why Gauss is important. Gauss method is actually deal with the, see, these two deal with the only when your coefficient matrix is going to be square matrix. These two, Kramer and inverse. Then you are able to apply. Otherwise, suppose your system of the coefficient matrix of the system of linear equation is rectangular, then you are failed. You are unable to apply these to Kramer or inverse. then you have to go with the Gauss. That's why I'm saying whenever you have a system of linear equation, just go with the Gauss. Gauss is tells you very simple way. Oh, Gauss is, what is the Gauss? So let me tell you this algorithm. Gauss is an Gauss elimination method is an algorithm which is based on row reduction. So just now whatever we studied, three type of elementary operations. In that operation, there are some row echelon form and reduced row echelon form terms came here. So many times you did already row echelon form and reduced row echelon form. The simple thing is, in the simple word, if I will say what is row echelon form, means you need to change your matrix. It can be rectangular, it can be rectangular, it can be m cross n. Change your matrix in the form of like this. If suppose this is not diagonal, it is not coming as a diagonal, so it may be like this can come. But the mean to say, whatever the entries here coming, the first entry, whatever the first entry is here, non-zero entry for the first row, below of all that make it 0. For the second row, if there is leading entry, suppose the leading is entry is here, so first make it 1 here, and below of all that it should be 0. And if the second row is here, then here the entry should be 0. These entries should be 0, and below of that all entries should be 0. Okay, this is the form called row echelon. What let me repeat again. If here is your non-zero entry, first make it 1, and below of all that it should be 0. Next, in the next row, your entry is coming here, not here. Suppose your entry is coming non-zero entries here, make it 1, and below of all that make it 0 using row echelon form. What I using type 1, type 2, type 3. Using these three types elementary row operation, try to make it in this form. In this form, actually this is the process to, this is called row reduction. I just telling you, I will tell you what is row echelon form or reduced row echelon form. So actually you are converting your matrix in row echelon form. Row echelon form is you are converting in this fashion what I am saying. If suppose here is 0, like here is non-zero, then here should be 0, because this is the first leading entry. That is called the first leading entry, pivot element. That is called also pivot element. So this is for the second row, this is going to be pivot element, and this should be 0. And below of all that, if you are changing it in row echelon form, it should be 0. So this is the process for the rectangular. If your matrix in not like a square, still it can be in this form, or it can be diagonal. It's diagonal means to say entries on the diagonal can come as a pivot element, and below of all that going to be 0. That means you are changing matrix in the upper triangular form.
So just a small doubt on this. So consider like the first entry, like first column, first entry is 1 and rest are 0. The second column, all entries are 0. And in the third column,
below of that,
no, like the first column, first entry is 1 and rest are 0.
Rest are 0. Okay. It is 0. All are 0.
No, column, first column.
Okay. Rest are all 0.
In the second column, all entries are 0.
All and okay. Yes. All and okay.
Column. I'm talking about column. Second column.
Oh, sorry. Sorry. Second column. This one all are 0. Okay.
All are 0. In the third column, the second place is 1 and rest are 0. So this is not acceptable, right?
This is
second. This is 1
and rest all are 0.
So, but we have to change here the columns. We have to interchange, right? Then only it will be acceptable, right?
No, no. It is correct. It is in row echelon form. There is no need to interchange here. Row echelon form is need to change the rows, not columns. So how you are saying the interchange need to change columns? So it is in the row echelon form. As you can see that I just now I am saying here is 0, as you said here is 0. So this is non-zero. So see that below of that all are 0. This is the form I am saying. Here this one is pivot element. This is leading entry, or in different word different pivot element, or in different word leading entry, which is 1 here, and below of all that 0. So it is in row echelon form. Now, okay. And now next is reduced row echelon form. So reduced row echelon form is one more ahead thing of this one. What is that? If suppose this is 1 here, or let's say, okay, if this is 1 here, so below of all that should be 0. Okay, and whatever it comes here, I don't know, but you can suppose here is 0 and here is 1. So it should be in row echelon form. So that means all r should be 0 here. But now if you are changing to in reduced row echelon form, means this is going to be pivot element or leading entry. So below of all above and up and down, it should be 0. So your matrix need to change in that fashion that if this one is going to be leading entry of this particular column, so below of all that should be 0 and above. This is only going to be the non-zero in that column. If suppose this one is here is no, so here is not going to be 1 here, because rest all r should be 0 here. So it should be lying here. All rest is going to be 0 here. So suppose here is 1, so below and above should be 0, and this is going to be in the non-zero. So in this fashion, changing in this fashion is saying to be the this is in reduced to echelon form. Oh, many times we have discussed, so no need to discuss more on this. I mean to say, when you are doing this, the main fact why we are this reduced row or row echelon form is needed for the Gauss elimination. Gauss elimination is exactly saying to be the you're changing your coefficient matrix in not only coefficient. That's the next word is called augmented matrix. And augmented matrix is nothing but your coefficient matrix, and you are adding an extra column like augmented matrix. Let's say B, I am saying augmented matrix of this system of linear equation means your coefficient matrix, and I am adding an extra column which is right side of the system of linear equation. You can erase this line. So this is going to be the new matrix. The entries of this matrix is the same as coefficient matrix as here, but the next column after finishing the the coefficient matrix, the next column is going to be your B side. This is called augmented matrix. And once you got that augmented matrix, change this augmented matrix in row echelon form or reduced row echelon form. That is called the Gauss elimination method or algorithm. It will help you to find it will not only find the solution, it will decide the solution when a system of linear equation has unique solution, no solution, or infinitely many solutions. So, and the no solution means directly in the R2, if your system of linear equation in R2, what do you mean R2 means? It contains two variables only, a b c dx plus ey equal to a b c d e f. So R2 means your variable in that system of linear equation contains two variables. So actually you have already deal with the coordinate system. So one equation represent a line in that, the another equation represent another line in R2. So if these two lines intersect exactly at one point, then you will say this system has unique solution. If you have a system of linear equation contain three equation with the same two variables, let's say some variables, some coefficients are here, anything, some equal to say. So still, if suppose this is happening, the third equation is went from here. This is, let's say this is L, this is L prime, this is L double prime. So this is L prime, this is L double prime. Oh, sorry, this is L, this is L prime, and this is double L prime, L double prime. So this equation represent this line. So in that case, this system has
no solution.
No solution, because it is not satisfying. It is not giving even a single solution. If unique solution means this line should pass through exactly the same point. In this case, you will say this system has unique solution. I am saying that the more general case, as sir have already this kind of thing, but I am saying in the 3 equation with 2 variables, I am saying, and if this case is happening, then it have no solution. And suppose you are lucky and your all 3 lines is represent the same, so all 3 equations represent the same line. Means this L1, L prime, L double prime represent the same line. It tells you that this system has infinitely many solutions. This is all about. So Gauss elimination is actually used to deal with the not only finding the solution, it used to decide the system has no solution, infinitely many solution, or unique solution. Let me tell you with a simple example. It will be easy to deal with that. I'm going to take an activity from the last one, because I just try to Gauss elimination. This one is very important, means it will deal the all kind of possibilities that system has no solution or infinitely many solution or unique solution. So I'm writing here, maybe let's do that. It will be very easy to, it will be clear, the whole thing, whole scenario. So let's say this is going to be this is minus x1 plus x2 plus 2x3, x2 plus 2x3 equal to 1 2 x1 plus
x2 minus 2x3
equal to
minus
1.
1 or okay, minus 1, and
equal to minus
3x2 and cx3
is to d.
3x2 plus cx3 equal to d.
cx3
yeah, cx3 is equal to d. Okay. So this is the system of linear equation. So matrix form of this system of linear equation is, write the coefficients in the entries as in row wise. So -1 1 2, and this is 2 1 minus 2, and this is 0 here. Here is 0 x1, you can think like this. 3c. This is going to be a coefficient matrix, and the variables, if you tell that this is going to be x, so x is going to be x1, x2, x3, and now b is going to the right side, which is 1 minus 1. So this is kind of ax is equal to b. This is the expression. If you say, somebody says that it is going to be the matrix representation of this system. So simple way is just multiply the matrices, and whatever you are getting the equation, that's all you can say. If it matches with this matrix, so this equation, you can say that, yeah, okay, correct, this form is correct. Okay, so this is the thing. Now augmented matrix is, just now I said, let's say I am saying B is augmented matrix. That means write the coefficient matrix. Okay, I just write this 1 minus 2 0 3. See, now if you want to give line or not, it's totally depend on you. The next column is going to be now B. So this is the augmented matrix of this system of linear equation. Now next process is, so Gauss elimination. What is Gauss elimination is, you will convert this augmented matrix in, it's totally depend on you. You want to convert in the reduced row echelon form or row echelon form. So my suggestion is row echelon form is enough itself to deal with all kind of like saying to be a unique solution, no solution, or infinitely many solutions. Reduced row echelon form will take time. Like you have to do twice of the same thing, or like you have to make it above to 0 also of the pivot element. So better way is just change your augmented matrix in only the row echelon form. Like here we can do it. So like here is C and D is given. So actually C and D will decide that, like if you will give some particular value to C and D, it will decide it have no solution, infinite solution, or unique solution. So you can deal with this itself equation whatever we will get. So let's do that. It will be more clear what I want to say. So suppose this. So what is the process to make it 1 here? So minus R1. This is going to be 1 here. Minus 1, 2. Sorry, minus 2, and this is minus 1. And this is 2, 1, minus 2, minus 1, 0, 0, 3, C, D. This is the operation. This is, you can say, second type operation. What I am multiplying here? Multiplying minus 1 in the first row. Now next is, here is 1, make it below to 0. So this is going to be 1, minus 1, minus 2, minus 1. Here is, what is the operation there? 2 times R2 minus 2 times R1 minus, sorry, what is R2 minus R1. So this is going to be 0 here. This is minus, this is 2, and minus 2 is going to be 3 plus here, and minus 2 here is minus 2, and 2 is minus 4, and then plus added 2. So this is going to be 2. Yes, this is going to be 2 minus 2, and added here it is going to be 1 here, and here is already 0. Please correct me if I am doing wrong calculation. A1, 2, 3, 4. Now here is you got 0, 0, make it 1 here. So what is the 1 by 3 R2? So please you should also calculate
second row, third column. It should be 6.
It should be 6 here. Here.
Yes, 2 instead of 2.
Okay.
Now here is minus, and then minus and added to this is going to be plus. So minus 2 plus
minus will
2.
be plus.
That's why it is going to be 2.
Okay.
Plus 2.
So now next
this will be for R2 plus 2 R1.
R2 minus 2
minus
R1.
4.
I'm doing R2 minus 2 R1 because I want to make it here 0. That's why 2 times R1. So the next process, if you want to do like this, you can do. But now let's tell you that no need to go always with the very basic thing. You can directly jump that. What you can do, no need to go divide by 3. Just R3 minus R2. You can directly do that. What you will get here? 1 minus 1 minus 2 minus 1 0 3 2 1 and 0 0 here you will get. This is going to be C minus 2 because you are doing R3 minus R2. Exactly, you are just subtracting R3, R2, R3 and R2, and this is D minus 1. This is you will get. So now what you can do? Now you can change it as the next operation. If you want to make it 1, so R2 by 3, you want to do that, you can, or let's leave it here. No need to that. So see, this is not in row echelon form. This is not in row echelon, row echelon form. Still, if you want to make it here, need to be make it 1. But we will not do that. Now I will convert this matrix back to the system of linear equation.
Sir, is this process okay, sir?
This is totally depend on you. That's why I'm doing.
Because we think that first we should make more one, and then
these are the process. But still, you can do like final thing is just we want the solution.
Okay.
You can back to from here itself. Still remain to one thing. From here we will decide something. Then we will back to the system of linear equation. So here is some telling something more. Let's say this is 3 here, 0, c minus 2. So this here something is more that, like, suppose what is the case happening, assuming c equal to 2 and d equal to 1.
Then it will be 0. This
It is going to be 0, 0.
0, 0.
You will get here 0, 0.
How that's c equals to 2?
No, I am just assuming. Assume case. I am making here case 1. Assume.
Okay.
Assume c equal to 2, d equal to 1. So you will get here 0, 0. So in this case, in such kind of case, meant to say this line, if it is following like this, below of all that 0 and above all that non-zero, or maybe this line can be here if all below of that all 0. I mean to say if such case is happening, in this case, this system has infinitely many solutions. From here directly you can tell. Otherwise, if you have confusion, no need to, like, you forgot this from here, you don't know is having infinitely solution or not. No need to confuse. From here, just back to the system of linear equation. What is going to be system of linear equation now? What is going to be
x2
x1 minus x1
2x3
sorry x2 minus 2x3 equal to minus 1. 3x2 plus 2x3 equal to 1. This column tells you the right side, and this side is come as a coefficient. So from here, for this form, I am writing the system of linear equation, and these two you got, and rest all are 0, x1 plus 0, so no need to write like this, right? So this you got from this matrix form, you got this system of linear equation. Now if you see clearly that it is going to work as an independent variable, x1 minus x2, like here this one is 3x2 is equal to 1 minus 2x3, or x2 is equal to 1 by 2 minus x3. So you say that 3 work as an independent variable, depend on independent variable, and x2 is going to be depend on x3. And if you substitute here, and x1 is also going to be depend on x3. So that means from here you can tell infinitely many solution, or directly from here also. If you are confusing with this kind of thing, like augmented matrix, now if you know that, so now you know the word rank. All of you know that a word rank. So let me tell you in the word of rank. So if now let me divide with this. Let me write this line. This side is your coefficient matrix, and if you erase this one, this is going to be your augmented matrix. So this is your coefficient matrix. The whole thing is your augmented matrix. So if rank of A equal to rank of this augmented matrix, I am denoting it by B. If such case is happening, see that what is going to be the rank of A here?
Internet banking user ID and password.
So maybe you are so many things maybe match. Let me erase with this rank word. So actually the rank is very easy to decide all things.
It will be
so actually rank of this
number of
Sir, could you just give that relation? Just
rank is 2.
Yes.
Actually, so if you know the properly thing is
Disconnect
rank
all
of
these things.
Actually rank, why you are studying the rank word for the matrix is actually uses that rank word uses Gauss elimination. Gauss elimination uses rank word. Actually rank of this coefficient matrix, if the case is rank of A equal to rank of augmented matrix B, in that case the condition is rank is less than that order, that number of this row. Suppose this is 3 cross 3 cross 4, number of less than row. In that case your system has infinite many solutions. It may confuse you because there are so many conditions. So let me no need to write this. Maybe you may actually this is the more thing. No
Can
need
you
to
do write and explain?
it will denote to you. So no need to go there. So the thing is, if you are confusing with this thing, just go back to your system of linear equation. From there you will decide. Let me mute you all.
But sir, in this case, we can.
I muted you all. Who wants to tell first? Unmute.
Sir, rank of this matrix is 2, right?
Rank of this have augmented also. You can see that augmented matrix also have, and coefficient matrix also have. Both have rank same.
Yeah, and the nullity is 1.
Nullity is going to be
1.
What is that?
That is.
Excuse me, sir. Since we're doing linear equations, there are 2 questions in activity 1.3 which are based on properties. So can you please clarify them?
Which one is?
So it's AQ 1.37 and 8.
AQ 1.3.
Yeah.
Oh, okay, so I will back to this. Let me finish this. Let me finish this one.
Can I interrupt once, please? Can I interrupt once?
Yes,
because
yes,
you just was speaking something about rank of A being equal to rank of B. Then what is it that satisfies that part? Is something I missed. Can you just?
I will tell you. No need to go there. That is not a new thing. That is whatever you studied rank word. The same thing is happening, but it is a different approach to telling infinitely or unique or no solution. So whatever you did for this thing is only leave it for the rank. I just use the rank word, but no need to go there. Okay, whatever you know that for the Gauss elimination, deal with that. But yeah, there are a relation with Gauss and rank, and the relation is Gauss elimination uses the rank word, and actually if augmented matrix and coefficient matrix have some similarity in the rank, in that case the system tells you the infinite, no, or unique solution. There are some relation. You will know if you spend time. You can easily know it is just a view thing, but no need to go there. Okay, let me go with the next one. Case is here. My case is remain for the. This is the case for from here. If you are unable to decide, just back to the system of linear equation, and from there you will to decide. Okay.
So, sir, when you get 0 equals to 0, then we can conclude that has infinitely many solutions.
So here, that's why I'm making a line here. In this case, system has infinitely many solutions. Suppose your case is here. I'm assuming C equal to 3 and D equal to, or let's say C equal to 2 and D equal to -1, or maybe any different from 1. Let's say I'm assuming 2. So our previous one equation was C -2 and D -1. So as we assume C equal to 2 and D equal to also 2, in that case, what is going to be here? Here is going to be 0, and here is going to be -1. Okay. Now make a line here. What you will see that? You will see that
there is no solution.
This case is happening for no solution. Why it is happening? See, from here if you are unable to decide that, so what you can do, from here you are unable to decide that, back to your system of linear equation. So if you back to your system of linear equation, what you will get here? You will get this one, you will get this one, but now multiply, like now the third equation is what is going to be 0 x1 plus 0 x2 plus 0 x3 is equal to -1. That means 0 equal to -1. What it means that it tells you that no solution. Is it ever true? Never. It will never true. 0 equal to 0 not equal to -1. But it's telling that you are getting, after doing some operation, you are getting 0 equal to -1. In that case, it tells you that system has no solution. That's the difference. From here, if you are unable to decide, always back to your system of linear equation. That's I want to say.
Okay. So sir, can you say that?
Yeah.
If you're like, I'm just asking about third case only. You can go ahead.
Okay, let me finish the third cases. The third case is, let's assume C equal to 2 and or maybe C equal to 3 and D equal to 1. So your previous case one was c equals to c minus 2 d minus 1. So if you substitute value here, what you will get here? Here you will get 1 and here you will get 0. So in that case, what is going to be? It have unique solution, no solution, or infinitely many solutions? So see, in that case, it have unique solution. You will draw a line. See, again, it may confuse you too. So better way is just back to now system of linear equation. Now, if you back to your system of linear equation, what you will get here? The third equation is, say, first equation you will got the same as here. The second equation multiply with, assuming to be this, you will get the same. The third one is x3 is equal to 0. Or if you assuming d equal to some different number also, not 1, if assuming is 2, so here is going to be d minus 1 is going to be 1. So x3 is going to be 1. So once you got x3 is equal to 1, you will substitute in this equation, you will get x2 is equal to something. And once you got x3 and x2, substitute in the first equation, you will get x1. So what it tells that uniquely you are able to find x1, x2, and x3. That this is the mean to say the system has unique solutions. So whenever
can we say that, like, other than case 1 and case 2, if anything else is there, it will be a unique solution?
Unique solution.
Okay.
So whenever you are confusing with the thing, so best way is back to your system of linear equation. From there, decide that it have infinitely solution, no solution, or unique solution. Okay. From augmented to back to your system of linear equation.
Actually, sir, when the variable does not get any arbitrary value, then only it is a unique solution.
No, when the variable gives a unique numbers, then it means unique solution.
Means variable is dependent only.
Variables are so there is different thing. The variables are dependent variable or independent variable. So I hope all of you know that those operations, those things, those concepts. I just tells you, see, this is one thing and this is the same infer, but I'm not telling a different approach. I'm just giving the same thing can be decided with the independent variable and dependent variable also, or see, those things is also the same here is also related. You will change it to 1 and then decide that okay, it is going to be a pivot element or not. Or the best way is always the best way is back from the after doing some operation, after getting in the row echelon form, back to your system of linear equation, decide there, back to your system of linear equation, and there from there decide that it have no solution, no unique solution, or infinitely. It will never confuse you. No need to remember anything. No need to remember independent variable. Nothing. Just a process. Just a process. Okay. So this is all about the system of linear equation. That's all. That's all the Gauss elimination. And actually, this is the Gauss elimination. I'm not doing any different method. This is the Gauss elimination. The Gauss elimination says make it 1, go very formal, but it's totally depend on you how you want to go. You want to go with the formal or informal, because in hand you want a solution at the end. So this is all about.
So can you clear those two properties from AQ 1.3 question 7-8?
Okay. Okay. Yeah, I will back to that.
Sir, sir, how can we get a nullity of this matrix? Suppose last row is 0, 0, 0, because it's had 4 columns and rank is 2. So how will decide nullity of augmented matrix?
So never talk about the nullity of augmented matrix. You will not going to deal with that. Nullity of the coefficient matrix you will tell, right? Why?
Only coefficient.
Because see, you whatever you studied for nullity, you studied only for matrix, not for augmented term. Only for matrix you studied. So only go with the matrix. Augmented is also one matrix. but the question may be in different scenario. It should be asked that you have given a matrix, this one, what is its nullity, what its rank. It is not going to be asked.
Actually, sir, in the augmented case, their nullity doesn't come here because all value is 0 there.
Augmented case nullity will never come, no?
Yes,
augmented is just your representation. You are representing your system of linear equations.
Augmented means there some values are there.
Augmented is just the term uses in Gauss, and nowhere is the mean. Only in the Gauss uses the augmented word, and there is its uses. And Gauss is just a augmented is just a different representation. You are representing this in different way in a single matrix. You are representing. That's all. So which activity was?
So AQ 1.3, question 7 and 8.
AQ 1.3. 1.3. Oh, 1.3 means where is this one? This here. Oh, here is 1.3 means here. Which question number?
7 and 8.
7 and 8. Okay, this one. This one. Right? So what is doubt here?
So, sir, the answer is B and D for 7.
Sorry, your voice is breaking. Is it breaking for me or all of you?
So for everyone.
Okay.
Yes, sir, for everyone, sir.
Okay.
Sir, I'm unable to understand how those two are the correct answers for both the questions respectively.
Okay. Okay. The simple thing is here, you will tell itself your answer. Here x1 and x2, and the question itself says x1 and x2 be solution of the system of linear equation, this one. This is the matrix form is given of a system of linear equation where the x1 and x2 are solution. So here if you are confusing with the, I think you are not confusing with the, here the thing is in this form. X1 and x2 is solution of this one, and x1, x2, x3 in this fashion. Are you confusing with this one? In this variable or the word solution? Are you confusing with this one? See, x1 it means a, it says solution means ax1 is going to be b, ax2 is going to be b. Here is x1 is not x2, these are not variables.
Okay.
Here
sir.
x1 means x1 this kind of how many variable means how many coordinates came here, right? Here x1 means coordinate, not only a single variable. This is not here variable. Here it contains coordinates. Coordinate means here matrix. X1 is actually a single matrix. S2 is also a single matrix, column matrix.
All right.
Got it? So this is and solution means ax1 is equal to b, ax2 is equal to b. If such case, this is the infer from your question. Now talking about x1 plus x2, is this going to be a solution or not? The simple thing is, if you want to check, see, you already deal with the, like you already know that, suppose you have equation, let's say x2 is equal to x plus 2 is equal to 5, and somebody says 3 is solution of it, or maybe let's say 4 is solution of this equation or not. So what you will do, you will substitute here 4 plus 2 left hand side and check that is it 5 you are getting now or not. You are getting 6 here, not equal to right hand side. Then you used to tell that, oh, 4 is not a solution of this equation. The same thing is, somebody says this is solution of this equation. So what you will do, you will substitute here. So substitute here x1 plus x2. Take the left hand side, sorry. Left hand, take the left hand side, substitute here. What you will get here? The next one is ax1 plus, sorry, ax1 plus ax2. You will get this one. Now this is whatever the information is given, which is b here, this one is b here, so you got 2b. So is b equal to 2b? No. So you will not say that, oh, so x1 plus x2 is not solution of this equation. It can be, solution of ax is equal to 2b. Not it can, it is the solution of this, right?
Yes.
It is the solution of this, but it is not solution of this. So very simple thing, as you used to do in the standard of 6 standard, 7 standard, the same thing is here. Nothing is different, because this is also one kind of equation. You are not dealing the linear equation, you are dealing with the system of linear equation, that's all. But still it work as a very simple way, as a in a simple as here.
Sir, this would hold true if b was 0?
If b is 0, then it will be true. If b is 0, then it is true, because when you substituted b here, you got 0. 0 is equal to 0. You are just satisfying, you are just checking, right? Is right left hand side is equal to right hand side or not?
Yeah, but it cannot be a general rule.
But it cannot be in the general case. Okay, so the next one is same thing. Now I am leaving to you. You need to check yourself. The same. I just said you need to check here, as here is saying the same process. One by one, you can do left hand side, right hand side, and can check. So this is still week 2 all about. The next term is the elephant thing is vector space.
Yes.
So let me try to finish it some more. So vector space. So vector space is nothing but a set with some property. Let me give it a different approach. Maybe you will get that idea.
Your voice is fluctuating.
Okay, now it will be clear. So all of you know that mod 5 something word or mod 10 something word. All of you know that, like I'm writing 7 mod 5. What do you know that what it means? All of you know that? 2. Right? It give all of you know that, then I will. It means that you will divide 7 with 5, and whatever the remainder you will get, you will write here. So that means 7 mod 2. I'm just telling a different approach to understand vector space. If you deal with the so many things like the R2, R3. I'm just giving a different example, but I'm assuming that all of you know these things. Okay, so now what I said, take the see, all of you know that is z is the collection of integer.
Yes.
So what I am saying, I am writing z5. What it means that each integer, it means that z mod 5. Z mod 5 means what it means that, see, z represent a set. So what it means that you are collecting those. Wait, not okay. Let me different.
We are collecting 0 to 4 every number of times.
Yes. So what I will tell you. Remainder z mod 5 is that z mod 5, or let's say natural number. If we'll say, let's deal with the natural number. Actually this comes in the linear. Let's say natural number, all of you know that. So natural number mod 5. So that means if you are, I'm writing mod 5 natural number means, that means each natural number, if you want to divide, you can you divide with the 5, and whatever the remainder will come. What are the remainders will come? 0 come, 1 come,
1, 2, 3, 4.
2. Till here this one come, right? So this set can be notated as I'm giving the different notation here. This is the wrong notation. Actually, the proper notation is natural 5 below to the like this. So no need to notation, whatever the notation. I just said that this is the set here. Now this is the set here. Okay. On this set, I am defining a relation.
I have a doubt, sir. Actually, in N0 in maths one, sir told that N0 includes 0 also. Right now.
N0 includes 0 also. So include that, no matter. If you include, you can include that, and the remainder still you will get in this set only.
Yes,
whatever is written here, whatever the remainders, here the remainders, all the remainders I listed here. Right? So this is the collection of remainders, I make a set here. Let's say this set is B. Okay. Now on this set, I am doing the same operation. Same. Addition, simple addition. Okay. I am giving a simple addition. You can add these two numbers, 1 plus this one or 2 plus. So I am giving a addition, but the addition is after doing addition, you will divide that. So this notation I am giving it plus below 2 in the what is called this is below to 5. And this, what is suffix?
Subscript
plus suffix plus suffix 5. It means that you will add these two, 3 plus 4. You will get here what 7. Now means here I 5 wrote here means now you need to divide and write the remainder of it. So what is going to be remainder here? What it tells there? If I wrote this operation like this, so what it means that? Means you will get 7 and divide with the 5. What is remainder? 2 remainder.
2.
So see that I am telling a different operation. I always used to deal with the plus, minus, and then see this is a different operation on this set. Right? Now this is one operation. I am giving another operation. What is that operation? Multiplication, you know. Now I am writing here suffix 5. So what is that? What it means that you are multiplying these two. I am writing like this. What it means that? What is going to be the answer for you?
Into 4 by 5.
By 5
and the remainder
2. So this is going to be 12, and so this is answer will be 2. Right?
Yes.
3 into 4, 12, and 12 you will get, divide 12 with the 5, you will get 2 times 2.
Remainder 2.
Remainder 2 you will get here. So see that what is happening here. So actually this is the property. So this property, this the closure, you know, closure word. So in vector space, I just said V here. So see, this is the different operation. This is the different operation on this set. But this operation, see, what I am doing on this set, I am doing operation plus this operation. If you check that this operation is closure. Like if you add closure means if you add any two number, if you
belongs to the same set.
Means A plus B, if you do any, A belongs to B, B belongs to C, B. So if you are do this operation, it will be an element of P. This is the mean of closure. Now with respect to, so let's say this is closure with respect to addition, because same sign I am using plus kind of, but there is modulo 5. Now next one is, this is closure with respect to scalar multiplication. Now let's say V over R. Now we fixing the field here, as you know that field is field R. Our field is R. So if you take that field over R, any real number, let's say any real number, let's say 7 from R, you are saying 7 times take an element from this set V. Now do the multiplication. What you will get here? Whatever the remainder will come, it will surely lie in this set. Right? Because you are dividing with the 5. Any number will come here. Right? If you divide with the minus also, minus is, still minus will work, right? Minus 5, let's say, because let's say minus 7 into 3 with the 5. What you will get here? Minus 2.
1.
So what you will get here, remainder?
-1.
-1. It's not working.
So you will get here 20, right? -1. So our -1 is not here. So what do we mean by that? Oh, so we are going
It's
to
not
wrong.
kosher.
Sir,
No,
our
no.
parent set is natural number, na? So that's why.
So yeah, actually, so okay. So we are
So
not
it is out
reaching
of
the vector
domain.
space. Yeah, but actually this tells you that now the thing is, this is not going to be for the any general case here. So this is not a this scalar multiplication is not closure for the general case, like, because just now we check with the minus. So this is not closure with respect to this operation. When you got this kind of thing, then you will say, okay, so v is v over r, okay, with this operation is not a vector space, not a vector space, because this is not closed the closure property are not closed under scalar multiplication. Actually, see, there is okay, no need to tell, no need to tell here. So this is not going to be closed under scalar multiplication. So that's I mean to say there are different. See what I am doing here. I have a set. I defined a operation here, different operation, and what I am dealing, I am checking the closure property of this set with respect to this operation, with respect to multiplication operation. If it is happening, if suppose this is going to be tree, this is going to be an element of it. Now the next, the remain 8 property. What is that? Associativity, identity, inverse, where then after this one, v1 plus v2 kind of, this is av1 plus av2, this property. The next one is avv, which is avv should be happen if it is happening like this, this one. And then these property, if it is happening, the rest is this is one. Let's say, okay, one by one, if I will write. The first one is commutative. What are those properties? I'm forgetting something. Let me see that. What are the properties here? 3. See why I give this operation, not only the plus or minus or multiplication. There are some different operation can possible to deal with the set. I just given a different operation on a set. Where is solve with us? So see, solve with us. Now here, let me tell you that the closure, this one, closed under, that is called closure or closed under addition. So we checked our for addition, it was dealing that, but we checked for scalar, closed under scalar multiplication, our set is not following that. If you are lucky that multiplication, that whatever the operation I just gave there, so whatever the operation I gave there, if suppose you are lucky that it is following, not only this one is also this associate, this is commutative called, this is associativity it is called, and third one is zero element will there, inverse will be there, 1 dot v equal to v, and this one, this, if these all properties satisfied by this v with these operation, if it is happening, suppose it is happening true, what I can see, that what I can tell you that, see, you can, that's why the over z mod 5, if you write like this, na, so it will work, minus 5, minus 3, minus 2, minus 1, minus 4 also here. If we collect
Sir,
this,
may I ask a question, sir?
Sir,
Sir, why vector space is so important?
Vector space is important because of the linear transformation. Oh, why
because
linear
it is
transformation?
limited by the linear
Linear transformation is
That's why it is
defined on
important.
the vector space. And what is the use of linear transformation? Linear transformation tells you the matrix. And what is use of matrix? You will use in data science. What is the use of there? You are dealing with the arrays.
Actually, is it help to sorting the data types or something like this?
So in there, in Python already that you are dealing with the adding matrices, adding, that there are some algorithms.
That means the vectors means all the lengthy data are there.
Vectors means that's why the sir have uses the vector as a column, as a list of some number, and said that this is matrix.
Number,
this is a vector
or something.
That's the reason here. That's why you are studying the vector space with the but see. So if you are something studying, then you need to learn it with a very formal way, right? That's why the terms came vector space. Then after reading the vector space, the terms came linear transformation. After reading the linear transformation, you know that the matrix representation of a linear transformation.
Or we can, other hand, we can say it is a condition space. By some conditions applied there, the linearity is satisfied.
So that is a specific thing. Like I'm saying, why you are studying? Why one by one steps we are reaching to in the data science.
Because first time when we heard this, when we listen this term vector space, we are very confused that what is vector space and how we can use this in a further time.
Okay. So let me finish that. So suppose your V is like this, and you are lucky that your operation whatever I operation gave here, satisfying these properties which we talked about here. If it is, then this set is this set is vector space with these operations over R. That's all. For our case, it is not happening, but actually this is true when we replace. We did for natural number, right? If we remove this natural number and work for the Z, that is called Z5. If you deal with the Z5 means Z5 means -5, -4, -3, -2, 0, 1, 2. Not -5 here, only -4, -3, 1, 2, 3, 4. This set with this operation, if you check that, it will be work as a vector space over R. Because now see, our problem was the minus thing, but I removed that problem with the minus. I added the element in the minus in that set. Now if you assume this V, so V over R plus 5, and these two operation is going to be, if you apply on this, and if you check these properties with respect to this set, actually forms a vector space. So this is a totally different whatever you, I don't know sir have taught about this or not, but I mean to say, whenever you are a set, somebody will give you some operation, and in that operation you have to check these properties and then decide that set is forms a vector space or not. Let me see that somebody have raised.
Very good example, sir. Till now we don't know this one, and it cleared many doubts. This modulus stuff we don't know.
Sorry, Nachiket. Which
yes,
one?
it's good example that modulus what we have done na, mod 5 plus operator and into operator. It cleared many doubts, and it's a good example for this introduction. We don't know this, so we somewhat difficulty we achieved, but now it is very clear.
Actually, that's why I want to tell that only dealing with the plus and minus in R2, R3, it doesn't make clear to you what is happening. Because when you see somebody says V over R and just given V of X, Y, something is some big operation. If you see that some examples are there, but still it will work as the same as in R2, R3. But this is a totally different operation. So that tells you a scenario what is happening behind it. Now, if you check this V with these operation over R, this will form a vector space. And
so
identity.
V is integers, right? Z.
Now our I applied modulo on Z.
But
modulo.
our weight is real number, right? So it can be anything like 2.5 or something.
No. So when you come to the real number, then this modulo, the remainder will not work, right? Because remainder thing is work associated with the natural number, is this thing, integers, because you will get a distinct, right, discrete number. But real number will not work, will not help you. So that's why I just back to here Z5 or N5.
Okay.
So so now actually this is Z5 called Z5 it is called. And if you collect this set, forget about this, I just collected this V, so no need to Z5 call it Z5. I just collected this V with, I defined some operation here. If you check this operation, it will satisfy, it will form a vector space.
Sir, Hassan here. Sir, I have a small doubts. Can I ask?
Yes.
So here we have two operations, that is multiplication and addition.
Yeah.
If these two operation satisfies, then all those 8 conditions also get satisfied.
No. That's why always you have to check this whole property.
Okay.
Always you have to check see, if I will make a criteria.
Yeah.
So the criteria is first check these two closed property. Okay.
Yes.
After checking these two closed property, check this identity and inverse thing.
Okay.
Because the numbers used to come from real number, so commutative and associative it usually happen. But zero, finding the identity element, zero vector,
Yes.
finding the zero or finding the inverse will not always, like, not in each set you difficult. So difficult means not easily to find, or maybe it don't have that set. So criteria is check these two, then back to this zero and inverse. And sometimes these also helps in this one sometimes, but it's depend how your multiplication. Suppose your multiplication is very differently defined, then see, after checking this one, you can jump to here checking this one.
Okay, sir.
Because here this one deal with the multiplication. See that this is dealing with the scalar multiplication, these two.
Yes, sir.
And if you suppose the operation addition is defined some differently, so check this zero vector and inverse vector, because zero, see that this operation deal with the plus, right? So how the operation makes difficult to you, check after checking. But the thing is, first check these two property, then check these two. Many times these two itself neglect the many options.
Okay, sir. So we have to must check those two operations first, then the inverse and zero addition,
and then this multiplication, and then rest all you can check. Then in the last you can check the that is commutative and associativity.
Okay, sure, I got it. Thank you, sir.
So this is the criteria. If you like in the merit form, if you want to write it, like this will come in first merit, second, third one. So this is the difference. This is the called vector space. On a set, you are defining an operation, and that operations satisfying this property, you will just call it as a vector space. And once, now see, before that it will say, without checking that, you will say these are the elements. Okay. But once this forms a vector space, just name it as a vector. So just call it a vector because this forms a vector space. So elements work as those elements, you can name it as a vector. Okay, this vector, this vector, this vector, this vector. That's all. Vector and element, no differences. Your set is not forming vector space, then work as an element. But once your set forms a vector space, that elements become vectors. Those elements you can call as a vector. That's all. So vectors are nothing but the element of the vector space. So once you know that, so now the name, the different things came, basis and dimension. I think so. The next one is so all of you the very much familiar with the vector space. I just gave a scenario of it, some properties. That is the thing: linear dependence and dependence. So I hope it is clear to all of you what is vector space. You have already did week 1, 2, 3, 4. We are just revising it. So I just told you what is vector space. So once you done with the vector space, so after getting this, in this vector means elements have some property. What would those property? So property is the term in the property term comes as a linearly independent and dependent. What is the then differences? What do you mean by linearly independent dependent? Suppose I am calling it this V1, this is V2. So dependent and dependent, like saying to be V1 and V2 are independent means V1 can be never written as a scalar time multiplication of V2. That's the mean. If V1 equal to some scalar, some real, like some real number, you multiply with V2, like let's say V2, V1 you are writing V1, or let's say okay, you are writing V2. Let me erase it. You are writing V2 with some multiplying, let's say 7 times V1. This is not dot. Dot means we are writing the operation here. We are writing as cross 5. So you are dealing with that. So 7 times cross 5. If it is happening, then you will say V1 and V2 are dependent. If it is not happening, then you will say V1 and V2 are independent. That's all. This is the only difference. So if it is happening in the each element, like what is happening here, let's say this is V1, this is V2, this is V3, 0 is never. 0 vector is always a dependent vector. You can think it as a what is something word is name? Intuitive or something name is when 0 vector is always a dependent vector. Yeah. Sorry for interrupting. Yeah, you can tell. Yes. Bhavna.
So one vector is a scalar multiplication of other vector. So it is dependent.
It is dependent. Then it is to dependent means you can tell V2 is depend on V1.
Yes.
So suppose zero vector is always dependent. Let's say this is V3, this is V4, whatever you want to say. If the case is happening, V1, V2, V3 is independent to each other, means V1 can never be written as some scalar V2, or V3 can never be written as scalar, or not only this one, V1 can never written as some scalar alpha V2 plus beta V3. If it is not happening these cases, then you will say V1, V2, V3 is independent. If it is happening, it is equal to some, you are able to find V1 as linear combination of, so that's the word came linear combination. Means you are linearizing means adding, linearizing means linear in the linear form, linearizing with the scalar multiplication. So means you are able to get the vector V1 as a alpha time V2 plus beta time V3. In that case, these three vectors is going to be dependent. So it is happening like that. So there is a formal definition. If you want to check V1, V2 and V3 are independent or not, the simple way is assume equation alpha time V1 plus beta time V2 plus gamma time V3. Assume an equation this is equal to 0 if after solving this equation, you got that alpha is equal to 0, beta is equal to 0, and gamma is equal to 0, then you will say these three vectors are independent. This is the formal way. This is the formal way. Whatever I said, this is the same same thing it is saying. Okay. So this is the formal way to saying that these three vectors are independent. If any one of them is non-zero, then the vectors are going to be dependent. V1, V2, V3 is going to be dependent. This is the definition, formal definition of independent and dependent. Okay. And also, whatever you right side, if you see that this right side is called the linear combination of V1, V2, V3. Somebody says write the linear combination of the vector a simple example. Now let me give a vector space here. So as I just said, it is going to be a vector space. So let's say write the linear combination of -4, 1, and 4. So let's say v1 is equal to -4, v2 is equal to 1, and v3 is equal to 4. So somebody says write the linear combination of v1, v2, v3, where linear combination, somebody says linear combination means he will surely give the scalars alpha, beta, gamma. So said alpha is equal to 4, alpha scalar means come from real number. So he said alpha is equal to 2, beta is equal to 2, and gamma is equal to 2, and said that find the linear combination. I just given this one alpha, beta, gamma. So what you will do? Sorry, 2 times -4 plus 1 time, sorry, this is also 2. So 2 times 1 plus this is more here means we are multiplying this operation we are doing. So please be careful with the operation. 2 cross 5 modulo 5, okay, and 2 cross modulo 4. So this is one kind of linear combination. Linear combination means just writing the vectors in this fashion, multiplying with a scalar and adding. So that's the meaning, linear combination. If the linear, okay, so this is the linear combination. Okay. So all of you are getting. I hope I am able to recall. This is the revision. I am able to revise your concept. That's the mean. It is fulfilling the that the title name of this session or not. I don't know. Is it fulfilling to all of you?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, is it completely fulfilled?
Sir, one more thing I wanted to ask. Like for statistics, we have been given weightage according to the week-wise content for the final exam. So for mathematics, will we get the same?
So I will say not week wise. Let's say I'm making a linear combination of weeks. I said linear combination means week 1 to week 8, the weightage is 50%, and linear combination of week 9, 10, 11 is weightage is 50%. That's all. This is the weightage. Okay. So this will I will tell. Not each week the weightage telling to be the each week as a weightage. I just make a linear combination of weeks and said that before quiz 2 will cover 50% and after quiz 2 will cover 50%. That's all the weightage.
Okay, sir. Thank you.
So this is the all about the linear combination, and so the next term is I hope all of you got that also, the linearly independent and dependent. The next term is span word. So span word is totally depend on the linear combination word. Span word is nothing is just what I mean to say. I'm writing my same v as -4, -3, -2, 1, 0, 1, 2, 3, 4. This is my set. So this is my set, and this is I'm assuming my operation. Okay. Now, span. Somebody says span. So what I am saying, see, this is a set with these operations. Field is just one-sided. Scalars come from here. So I take a subset here, any subset. Let's say, so that's why I'm making, writing to be the specific, I'm saying v1, v2, v3, v4. v1, v2, v3 means vector. It is anyone can assume, like v1 can be 4 or v1 can be 2. So I'm making a set from this. This is a subset of v. Okay. So what I am saying here, span of yes. What do you mean by this? I just now said that linear combination word. So linear combination of these vector means alpha time v1 plus beta time v2 plus gamma time v3 plus delta time v4. This is one linear combination. If you give the specific value to alpha, beta, gamma, delta, it will give a vector. Similarly, if you change the values to alpha, beta, and gamma, it will give the different vector. It will see this is the sum. So sum here is 5. Please, so please be careful. This is modulo 5 word count. So 5 plus 5 plus 5 modulo plus 5 modulo plus modulo 5 plus modulo 5. So if you just give the value alpha, beta, gamma to the alpha, beta, gamma, you will get a vector. You will get a from after doing that, after doing this addition, you will divide the form. You will get a element from here, vector from here. So it will a single vector. Okay. So collect. See, this is the linear combination. General linear combination. I give any value to this alpha, beta, gamma, delta. So one by one, I am just giving to alpha value, beta value, gamma value. One by one, I am giving to value here. I'm listing here one by one. Okay, I am just listing here all possible values, all possible, whatever the possible value. I itself I don't know how many values going to be. It's going to be infinite. But yeah, I just listed here. Okay, I just listed here. Now this span is exactly equal to P. Okay, so that's the word came. This yes is actually a spanning set of okay, I'm missing. I think I'm missing some word. Let me
Can I give an example, numerical example, and it's general concern?
let me check the word, proper word, then I will be. I think I'm missing some word. That's it. Let's solve it itself. Linear combination, dependent and dependent.
Maximum linearly independent set.
So the maximum linearly independent. I think I'm missing. Okay, just 1 minute. Or maybe spanning set means. Spanning set means this yes able to span whole T. Okay, fine.
Contains all the possible vectors in the given space.
So given vector space. So yes is called the spanning set of B means. See, one by one you calculated all. Okay, one by one you calculated all possible. So if it is exactly equal to this contain infinitely many, but yeah, it's repetitive. So see, you know that in set already you have studied. Okay, you have already studied that. If elements are repetitive, then you can collect if in the set form, if you will write that, it will a single one by one. Okay, differently. So if you substituted this one by one here and properly listed that, if this is exactly equal to V, means here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, 9 there. If exactly 9 elements are coming in this span, when you span, exactly 9 different elements are coming. If it is happening, then yes is actually the spanning set of it. This is called the spanning set. Okay. If it is not, then yes is not a spanning set of V. That's all. If it is not collecting those vector which is in V, then it is not going to the spanning set of V. If it is collecting all vectors which is in V, then it is going to be the spanning. Now let's back to him. See, this is the finite vector space linked to V, but so I just wrote a very vague, or maybe this is very different. I just want to see very vague, or what I will say, not a proper correct. I just give it for the understanding.
So can you give one more example? For
So the best way is, now let's back to, or the more good thing is R2, R3. So this is a finite vector space, but I'm not sure it's saying to be finite word. I have to check it, but I just given an idea.
Combination of element.
Sorry.
Yes,
It
here
is
is
defined
a
as set of all finite linear combination of
linear combination is mentioned.
Yes.
A finite linear combination.
Yes, sir.
Of elements.
Oh, finite linear combination, finite linear combination.
So all finite linear combination of element.
All finite. So that okay. All finite linear combination. All finite means how many you are vector assuming you're listing
A
those,
set of all finite.
a set of all finite.
Yes, set of all
Yes.
finite linear combination of elements or vectors.
Okay, so no matter the word is, the thing is what I want to tell you. That is not a big thing. That is not a different, like not a wrong thing. The thing is what I want to say, if the set you're taking the finite or infinite, it doesn't matter. If it is depending that, yeah, that you are collecting those vectors in a set and in that set able to when you are taking the linear combination of those vectors and you are able to get that exactly b, then it works. Then you can say that that set is going to be that set is actually a spanning set. Now for let's back to the our case, like where for we are
In this case, we can say the span set also dependent set. That means the
so
linearly dependent.
spanning, yeah, a collection of vectors can be dependent. So that's why when the span word came, that's why the basis word come here. So let me tell you, if you just said that, okay. So if the vectors, this collection can be dependent or independent also. If you are lucky, not lucky, if this collection is collection of independent vectors. In
But
that case,
but I think if the span is independent set, but some part of the set must be dependent, and that's and the only these we can make the another vectors.
Okay, so what I mean to say, if see, we can be dependent on these three, means v4 can be written as v1 to v1 to v3 v3, but I just said that if this collection is like all four vectors are independent in this set, all four vectors are going to be independent, so still it is spanning. So that's why the word came basis. Basis is the collection of those vector, or maybe basis is a set which can span whole vector space. So here is spanning. If suppose someone is depend on it, then it can never be a basis. If all of them are independent, then you will say this is going to be a basis. Otherwise, any of like basis.
But sir, I mean to say, if a span set is independent, almost independent, the all with the
All are
volume,
independent. Okay.
also independent. But yet the some part must be dependent. Otherwise, it can never span.
Some part must be dependent.
Because that's why the linearly combination can be happen.
No, basis is a minimally spanning set, no?
Actually, the process is no. See, if you want to find a spanning set of a vector space, what is the algorithm sir said in the video? He said that take a vector, okay, write the linear combination. If collect in a
there is a eliminating process and
so eliminating process. If it is happening,
just
it is
write it
exactly,
as a matrix. No, that's better. RREF.
So if it is
but
happening,
in the definition, sir, in the definition, it is said that the define it is a define. It is a set is defined as the set of all finite linear combination of elements. If there is no dependency between the some set, how the linear combination there may be happened.
Linear combination, if those are the not dependent, means those are independent, and if any one of is dependent, means that vector is going to be the linear combination of remain those are. That's the word is uses here. Okay, maybe I'm not getting.
Span is a set of all possible linear combinations.
Yeah, all possible linear combinations.
So
all
it will
linear
consist of dependent vectors and linearly independent vectors. From the span, we will get the basis, that is nothing but the linearly independent vectors.
Span can contain the dependent vector. Okay, it can contain, but
it can contain dependent vector, or also it is a independent vector.
It may not also. It may not also.
Yes.
It can. It can not also. Okay, it can. Yes, the span can contain dependent vector, cannot also. Like for example, let me give to you a simple example.
But my question is, the some part of the span must be dependent. Partially, it must be dependent.
There is no word for some part of span means what? I'm not getting. That's why the some part of means there is no word for some part of span.
Suppose the span contains 3 vectors. Their 2 vectors must be dependent to each other. But while we take 3 vectors at a time, they are independent to each other. Is it possible?
Yeah, this can possible.
Oh, I'm just saying this.
So this can possible. Let me give an example. Like suppose you have a vector space here. I am writing yes as a 1 0 0 1 and 1 1. Okay, this is the collection of vectors. If you check that these two are independent to each other, these two are independent to each other, these two are independent to each other, but all three are dependent. Means this is a dependent set. See, vectors are independent to each other. Okay, but now if you check for linear combination of all these three are going to be dependent.
Dependent, yes.
Got it?
Yes.
Okay. Now, what is span means? If you take the span of this, yes, okay. So already you know that these two are, whenever these two heroes are available, it can generate whole R2. So yeah, this can generate whole R2. So this will work as a dependent on these two because these two heroes are here. So actually span of this is whole R2, but this is not a basis. This is not a basis. So I just want to say, you know that the word is linear combination, dependent, and span. What I mean, so span is the collection of all possible linear combination of the vectors, whatever span of a set you are saying. So span of S means collection of all possible linear combination of these three vectors. This is the span word. Okay. Now, if this set span whole, okay,
whole. Sir, I have a small doubt here. Span doesn't depend upon independent or dependent, na?
Span doesn't mean to be dependent or dependent.
Okay, sir. Thank you. Got it.
If this span, now this is span, yes, you are writing, this is the collection of all possible linear combination. If this span is exactly equal to this B, then this S is actually called the spanning set of B. Because B means it can generate whole R2, means whole R2 here. V means whole R2 for our case. Now, the next thing is, if this S is actually collection of linearly independent, means as our case here, this is just now said, this is dependent, you can check easily. If our S is the set here 1 0 and 1 1, only these two. If you check that these two are independent, now if you take a span of it, it can generate whole R2.
Whole R2.
Very easily you can check. Let me tell you the process also. Let me tell you the process also, maybe you will get idea. Okay, I'm saying this can generate whole R2 means what? Take a general vector from R2, okay, AB. Now I just said it can generate means 1 0 plus beta time 1 1. Generate whole R2 means alpha time 1 0 plus beta time 1 1 means I am taking a vector, means it can be written as AB can be written as a linear combination of these two, right?
Different lines.
So that means now solve this equation, alpha plus beta and beta equal to AB. I want to find alpha and beta. Our specific case is AB. I have a vector. I want to check that is this vector can be get from these two vectors or not. That's the meaning of span. That's the meaning of basis also. Okay. So this you got, this is the equation you got. Now beta equal to, you got B, and alpha is equal to A minus
beta.
B. Beta means B. Sorry. A minus B.
A minus B.
B. So if you assume, as you said, AB equal to belongs to R2. If you AB means, let's say A equal to 1 and or maybe A equal to 5 and B equal to 7. Okay. So what is going to be your alpha now? -2 and beta is equal to 7. So if you check that, if you write this here, you will get exactly this vector. Using these two vectors, you are able to get this vector. That means any vector, because whatever you got the relation, using this relation, you can get any vector. That's the mean of saying to be the spanning set of P. These two vectors can generate whole R2, and that's why so actually this spanning is S is actually the spanning set. Once you got S is a spanning, check their linearly dependency and independence. If those vectors are linearly independent, just say that yes is a basis. Yes is a basis. If not, if these vectors are dependent, then yes is not. No, yes is not a basis. Yes can generate whole R2, but yes is not a basis. That's the meaning of saying to be basis, span, these are. And that's the meaning of I want to tell this linear combination. That's the meaning, linear combination. That's the meaning, generating the vector. So got the idea what I mean to say, span or basis or linear combination or dependent and independent. So this is anything I'm missing. Let me figure it.
The last two things, that spanning set and basis, even we are getting all the vectors. Then why spanning set is not a basis?
The why not a basis? Reason is if suppose I just, okay, let me add here and 0 1 also here in this set. Let me add it here and 0 1. Now see these two enough to generate whole R2. I just added a vector here. It's still yes will be a spanning set of this R2.
Yes, it is still a.
But the condition, if you check this, these three are not linearly independent to each other. Sorry, these are linearly independent to each other. Like in this set is not independent. This set is not independent means you need to check alpha time 1 0 plus beta time 0 1 1 plus gamma time 0 1. If it is assume it is equal to 0, if alpha equal to 0, beta equal to 0, and gamma equal to 0, then this set is called independent set. If this set is not independent, then if not independent means not basis. Sorry, not what I did. I said wrong.
It means it is 0 only if alpha, beta, gamma is 0.
0. So if this set is independent, but our case is this set is not independent. This is dependent. So this is not a basis. It can generate whole R2, but not a basis. I erase it here. This vector I erase it.
Because it's the extra.
That vector was extra. Because of that, it is not becoming a basis. I erase. I remove that vector. Now this set is going to be basis.
It is a maximum linear independent.
That's the word, maximum linearly independent or minimal linearly.
Or minimal span set.
Minimal spanning set. Yeah. So,
is the basis unique for the given set of span?
So no. So for a vector space, there are infinitely many bases. For
element may be changed.
Like I just said 1 0. This is a basis of R2. 1 1 1 0 0 1 0 1. This is another basis of R2. 1 1 1 minus 1 is another basis of R2.
Because two lines in R2, two different lines.
The reason is actually why this is.
Okay, thank you.
Actually, the reason is you can check. The reason is just take a linear combination. Okay, linear combination of these two and take any general vector. If these two are able to, you are able to get such kind of equation and able to get the values of alpha, beta. then that's all. This is going to be a basis. And actually, for each two linearly independent,
Between two lines must be there, and their angle should not be 0.
Their angle should not be 0.
Yes.
Okay.
Then we can set the.
Actually, that is the case here. So the dimension word or rank word for the base for the vector space is number of element in the basis. Count the cardinal base dimension is cardinality of the basis, any basis. If you count these two, there are two vectors in the basis. So dimension of this vector is 2. So the thing is, if you are saying, let me tell you, suppose V is a vector space, and I said we have infinitely many, we have infinitely many bases. Okay, so let's say I'm saying S1, S2, S3, S4. Okay, these are the different bases of this V. But the condition, if you get the cardinality of each,
it must be same.
All are equal.
Yes, cardinality
will be equal. So if you are saying that this is a basis, this is another basis, this is another basis, but each basis have the same number of elements, cardinality same, and whatever the number you are getting, that is called dimension of the vector space. Got it? This is the process.
And it's also define. It's also depend on the function.
Depend on function.
Yeah. So what will be the cardinality? It's also depend on the function, sir, or no?
No, there is no function word. How you are associating with the function word here?
The cardinality. It's depend on.
So you are associating a function. Okay. Okay.
Yes,
okay.
sir.
Okay. So yeah, you can associate. Actually, if you are associating.
If there is no function, then it is dependent on the dimension also.
Okay. So one thing I want to solve an example on the term of subspace. That will be more clear. Hello. Yes, Ravi,
I've got, after this, I have one question. Let me ask that.
Yeah, you can.
So the thing is, right, if I am given a basis, right, how to find a function from it? I've been trying that. Yeah, let's say T, it's slightly in the 6th week thing. So let's say there is a basis given 1, 0, 1, 0 and 1, 1, or 1, 0 and 0, 1. Okay, the standard basis is given, and there is a transformation also given, say for a vector subspace. Okay, how can we find out which function? How to identify that function? Like you did write alpha plus beta.
Okay. Actually, there is so actually mean to say it is given like this: 0, 1 is equal to some vector is given, 1, 0 is something is given. So you want to find the mean to say what is going to be the expression.
Yes.
So actually, this is on week 6, and I'm trying to be till here only. This is on week 6. Actually, I already taught this the same process how to find this expression very easily. There is not a tough thing.
Alpha beta, no?
Alpha assuming to be the alpha beta and substituting, or maybe in the next session I can tell you the more, because it will take time. If I can quickly tell also. Okay, let me do that. It will
No. Take your time, and if it is in the next session, then I will attend that session as well. Okay.
Actually, the simple thing is, as just now said, what is here xy means xy this is any vector. So means you can write this vector xy as
alpha into
alpha into 0, 1 and plus
beta into 1, 0.
1, 0, right? So anyhow you will get the expression alpha as the expression of some function of xy. Beta is some you will get, okay, you got that alpha plus beta is equal to x. No. What is that? For this case, alpha is equal to x and beta is equal to y. So it's the same thing you got, like x here, y here.
Yeah.
So now apply t here both sides. Apply t here means 1 by t, as if it is not a standard. So the expression here can be changed. Here can be different function of x and y. Okay, some linear function. Okay, so apply t here. So t10, t01 you have already, and this is y here, t10. So you have already some vector. This already map is there. This already map is there. This one, and this is the expression. This is the process to get the expression. I just quickly told.
Okay, thank you. Just stuck on a couple of activity problems in section week 6.
So
week 6.
Actually, I want to ask I want to give there are the basis. If suppose you have I want to solve some example. Basis, finding a basis. If you have not only generally used to be in the subspaces. Mostly you will see the find the basis of subspace. So subspace, you know that nothing but a vector space. So I hope you know that what is the subspace.
Yes. So yes.
The main thing is finding the basis of a subspace. So like I am giving, let's suppose I am giving a vector space V which is R3 and a subspace W as X, Y, Z. This subspace is X plus 5Y plus 7Z is equal to 0. So if you check that, this set is actually a subspace of R3. The simple way is saying to be this is, now all of you know the tangent thing, or tangent of a function. So actually not tangent only, you know the plane. Actually this represents a plane in R3. So if you check that, this plane is actually will pass through origin. So the geometrically directly you can say, yeah, this is going to be a subspace. Suppose somebody is given here 1. So this is a plane, but not passing through origin.
Okay.
And in the reason is, if a plane is not passing through origin, so it is not going to be the vector space. The simple reason is, in this set 0, 0 vector is not there. The simple thing is, we check that here 0 plus 0 plus 0, you got 0 left hand, but this is 1 not equal, 0 is not equal to 1. That's the reason here this is not going to be vector space. So if a plane representing a subspace, it should pass through origin. So once you have this one, this subspace, the deal is here finding a basis, or what is going to be the dimension of this subspace. So what is the dimension of this subspace?
Number of elements.
2.
Dimension.
3.
Yeah, it's 2.
It's 3.
Dimension doesn't tell the variables, right? You need to find its basis and then the cardinality. So the process is how you will find the basis of it. So this equation will tells you the finding the basis. If what the vector, this W will collect vectors. This is the collection of vector which will satisfy this equation, right? Means
so if I say 1, 0, 0.
1, 0, 0.
Oh, and then 0, 5, 0, 5, 0.
0, 5, 0.
And then 0, 0, 7.
0, 0, 7. So you are saying this is a basis, but actually this itself, this is not an element of W. So that's I want to say, this is not element of W. This is not element. If this is an element of W, this should satisfy this equation. This should satisfy this equation. This satisfy this equation. This is not satisfying here. One you are getting from this one, you are getting 1 equal to 0, which is
so if that is the case, then the element should be like, let's say 1 plus 5 instead of 5. Let me do it.
1 minus
no,
5
let's start.
And
2, 1 and minus
1 minus 1 and This is 1 minus 1 0 and 7 will be okay. Oh no 0.
So,
No.
Yes.
so
Ah,
2, 1 and minus
still,
1.
I'm making wrong here.
1 and minus 1.
5 and minus 1 and 0 will work here.
Yes.
5 minus 1.
Check that. 5 minus 5 and
Yes.
0.
Minus 5 plus 5 and 0. Okay.
Similarly, you can check for
7 0 minus 1. 7 0 minus 1.
7 0 minus 1. It will work.
It will fit.
7, it will work. So these these are the vectors from this W. Okay, you are able to get some vectors here.
Okay.
Suppose you just got these two vectors. Check the independency of these two vectors. Is this going to be independent?
These are independent. If you do a row echelon, you will be able to.
Correct. These two are independent. So now, okay. So if you collect this in a set, 5 minus 1 0, okay, 7 0 minus 1. Is this set yes is going to be the span W or not?
No, sir, no.
No. How you are not sure, like how you are sure or not sure, or how you are sure that it is not?
X, Y, Z, at least 3 required to be for getting entire W.
No,
not needed because I'm looking at a question.
Okay, if you are assuming, if you are confused with, let's take a vector. Okay, let's take a vector from W. I am assuming same. Let's say ABC. ABC. Okay. ABC a vector from W. So if ABC a vector from W, it means A plus 5B plus 7C should equal to 0, right? Okay. The process is, I want to check is this vector can be generated using these two vectors. So assume that alpha time 5 minus this one plus beta time 7 0 minus 1 equal to ABC. Assume that. Okay. So it is 5 alpha 7 7 beta equal to okay
plus
1
comma
minus alpha minus beta, right? Equal to A, B, C. Just compare these two. So B equal to minus alpha,
C equal to minus beta.
Minus beta. So that means our main is to find the alpha and beta. So alpha is equal to minus B and beta is equal to minus B. Right? That means you are exactly able to find, for any general case, you are able to find alpha and beta. What it tells, these two can generate any vector, right? Because you have already.
Yes, it is a basis.
Right? Because this is a general vector and alpha beta can be generate any vector. That means span, this yes is actually spanning W.
Sir, there is one question here. Like this is x plus 5y plus 7z. It is R3, right? We are talking about R3, right? If we are talking about R3, then the spanning set can have only 2 elements.
This is in R3, but yes, this is a subspace of R3. So subspace can have less than vectors can generate, right?
Sir, how do we know it is subspace of R3? I mean, what is the difference? If in the same example, if had it been, subspace itself, so
see, that's why I said I just
elements, sir, because Ax plus 5y equal to minus 7z.
Okay, if it is x plus 5y plus 7z equal to say 10, then it will be R cube.
Equal to 10.
Yeah. Yeah, equal to 10. Yeah.
Then it won't be a subspace because it has to go through an
then
origin.
it is not a subspace.
It's not satisfied.
This is not a subspace. Reason is why from you I'm asking her why it is not a subspace if it is 10?
Because this will not satisfy because it is not passing through the origin, sir. Right?
Zero vector should be there.
It has to go through 0 0 0.
Right. That's the reason here.
Okay.
And see that what is happening. So you got some vector. After getting, you told me that these two vectors, and after, what is the finding of minimally spanning set. What is the process of finding the minimally spanning set? See, I used these two vectors. You can itself, let's assume only 5 minus 1 0. This is the vector. Check that it is able to generate any vector, or you will check that it will not generate. So next vector is you will added a vector in this. Is will able to generate or not? Yeah, actually it is generating. And also you check that these two are independent.
Independent or not.
So now this is going to be a basis of this stuff. So actually a subspace of R3 can have a dimension 2. Actually the reason is planes. What are the planes in R3 which is passed through origin represent a subspace have dimension 2. Have dimension 2.
Actually, this is a plane in R3 in 2 dimension only, right? Because we can convert X or Y in terms of Z or vice versa.
Yes, that's the reason.
Okay.
That's the reason.
Thank you, sir. Sir, affine space, there was a question in quiz 2. Can you please touch upon affine space also today, or you will do in the next session?
next.
Okay, sir. Thank you, sir.
Could you please find the basis from the equation x plus 5y plus 7z equals to 0?
So if from the equation, okay.
Yeah.
So x plus 5y plus 7z we have. From here, you just told me, I just checked it and find the this is a basis of the proof. But let's see that from the equation we can also get that. So what is the process that write this equation as you can able to write minus 5y minus 7z. Okay. So this in the video itself, sir said you can assume y equal to so we will get the same thing, y equal to 0 and z equal to 1, and substitute here. You will get x is equal to minus 7, right? So the vector, a single vector will be minus 7, 0, and 1. This is a vector you got. Now give a vector y is equal to 1 and z is equal to 0 in this equation. So you will get x is equal to minus 5, right? Now the corresponding vector will be minus 5, y is equal to 1 and z equal to 0. This is another vector. So this is also a process we directly jumped here, or this is not jumped. I actually just said it is that word that I just used. Otherwise, this is a vector. This is now if you collect this in a single vector, this is going to be a basis. Differently, just give to it y is equal to 1 and z equal to minus 1. You will get x is equal to some value. Collect in a vector. This is going to be a vector. Now you can get y is equal to 1 and z is equal to 0, and you will get some vector. So this is going to be another basis.
Is it same as basis of null space?
So actually what is happening here, not null space here is null space is
basis of null space.
Basis of null space. No. There is no word for basis of null space. No. Basis of null space. Oh, sorry. Basis of null space. Sorry.
Yeah.
Basis of null space for this equation you are saying.
Yes.
Particular this equation, it must be there because value 0, sir.
Okay.
Homogeneous equation.
Actually, this is a homogeneous equation, and actually, this is a system of linear equation whose coefficient is 1. Coefficient matrix is 1, 5, 7. So this matrix, this coefficient matrix, the basis of this coefficient matrix is actually null space of this matrix is actually the basis of happening for this. The proper word is saying to be like this: null space of this matrix, okay, or null space of the system of linear equation you are saying. Okay, null space is actually the solution space.
What we got, this is nothing but basis of null space only, na?
Null space of this matrix, or null space, basis of null space of this system of linear equation. This system of linear equation. Okay, fine, yeah, correct. Basis of null space of this system of linear equation. That is also. Yeah.
Sir, I have a
Because
doubt.
I really confused when we get basis in matrix from span, we'll write in a RREF form, and that rank related will be basis, right? That will become dimension.
Rank tells you the
dimension.
Dimension of what?
When we have a set of vectors, spanning set of vectors, we will write span vectors as a RREF, I mean in matrix form, and we will convert it into the RREF. And the pivots will become the basis, the corresponding pivot columns.
Okay. So in the basis of that spanning set, that whatever
Yeah,
you are
that will become dimension, right?
Dimension, yes, correct. That's the dimension of that spanning set. Which in that you are collecting.
So when this linear transformation is given, basis is nothing but the null space basis.
Linear transformation is given, and the basis, the kernel is different thing, no?
Because I really confused when this dimension word comes, basis and dimension.
Okay. Actually, there are so many null space for system of linear equation, null space for matrix, and null space for linear transformation. There are 3 terms, right? And rank.
When multiple choice is given, it's easy to sort out, but in case of fill in the blanks, a little trouble.
Null space means solution space, na?
Null space for the system linear equation is solution space. Null space for the matrix is the word is null space for matrix is exactly for null space. Null space for linear transformation is kernel.
Yes.
There are 3 terms. Null space for matrix is solution space. Null space for matrix is for null. That is the null space for matrix is the same. The third one is null space for linear transformation is kernel. Okay.
So here I have some doubt here. So we are seeing here 2S, which is the set of basis or this set. So we can get any number of basis, but the dimension of the basis remains same, na?
Dimension of the vector space is unique.
Yes, sir.
Dimension of a vector space is unique, but yeah, basis can be different. There are infinitely, for any vector space, there are infinitely many bases.
Yes.
Okay, so is there a need to solve some another example? You can tell.
If this equation is equals to 2 or 3 some number, can we do it similarly to get the dimension?
If
affine space.
If it goes to 2, if it is equal to 2,
if this equation is equals to some real number, x plus 7 by we solve, right? If it is equals to some real number, affine space.
If it goes to 0, if it is not a real number, then it will not go through origin. If it does not go through origin, it is not a vector subspace.
Yes.
Okay, so let me give if you are okay.
Affine.
Okay, I'm giving affine. I'm giving a vector x, y, z. Okay, this is 2 y. So and the relation is x is equal to, or maybe x plus y is equal to, okay, better way, x is equal to 2y and y is equal to, okay, I am asking question. Okay, 1 plus z. First thing is this one question from your side, or maybe z plus z plus 2. Okay, now the question is, I have this set. This is a set of R3, subset of R3. Okay, is this set is a subspace or not of R3? The subspace means addition and multiplication, whatever this father space have, will be apply on the. So is this subspace?
It's not subspace.
No.
Why?
Because
0
0
is
does
not
not satisfy.
satisfying.
Yeah.
Sorry?
0 vector is not satisfying here. 0 vector is not inside.
It is satisfying. Means here this is pass through origin.
Y equal to Z plus 2. 0 is not equals to 2.
So actually here is happening. 0, 0 is not in this subspace. The simple way speaking. This is satisfying, but this equation is not satisfying.
Not satisfying. Yes.
So actually this W is actually collection of two planes. One is from this one, and another is some not passing through origin. This plane is passing through origin, but this plane is not. Separate planes. So I assume that okay, this is not a vector space. I just erase it here, and now I just given 5, or maybe I write like this: 5 y plus 5 z is equal to 0. Now is this a subspace?
Yes, now it is satisfied.
Yes.
Okay.
Yes.
This is a subspace.
Yeah.
So the question is next: what is the dimension? What is the dimension of it? Can you directly say without solving? Just directly, without solving.
Dimension will be 2.
1.
Because Y and Z are
2, 1. How it will be 2, 1? Only single number.
Y is
Either
depend on X and Z is depend on Y.
The dimension is 1.
dimension
One,
is
sir. 1.
yeah, that's the correct.
Yes, yes. 1, 1.
Yes,
Yeah,
so 1 only.
yes.
X is
If is substitute the value of y,
X is equal to 2y and y is equal to minus 5z. This
yes.
forms a system of linear equation where z work as an independent variable. Okay, so in this system of linear equation, only one independent variable and rest all y and z, x and y are dependent on it. If you are inferring with the independent kind of thing, so using that, if you can directly tell dimension is going to be 1 here.
1.
And okay, the next thing is what? Tell me a basis. What is any basis? There are infinity bases.
1, 0.
1, 0.
2, 1, 0.
Okay, 2, 1, 0. 2, 1, 0.
0,
Okay,
0
let's
minus.
check that. Let's check that 2. Okay, it is satisfying. And
But it won't be a member of this thing, right? Because y plus 5z
it
is
is not
0.
happening in the of this, right? This is 1 plus 0. 1 plus 0. Yeah, this is not a vector.
No.
This is not a vector of it. 2, 1, 0 is not a vector of W. Not belongs to. So as you got this have dimension 1. So okay, I will. Okay, give me a basis of it.
2 minus 2.
So minus 10, minus 5 and 0.
Minus, what is that again?
Sorry. Sorry, so minus 10, minus 5, 1.
Minus 10, minus 5, minus 1.
1, sorry.
1. Okay. Is that satisfying? Minus 10,
Yes.
minus, okay.
Yes.
Okay, this is minus 5 and this is 5. Okay, yeah. So this is a vector of W.
Okay.
Yes.
So if you collect this vector in this set, do I need to check it? Do I need to check it? Is this spanning or not? I need to check it. Is it?
Yes.
Or
Sir.
from
Yes,
this
yes.
dimension, it can I can tell that this is a basis. So actually, what I mean to say, number of as you got the dimension is 1. So and you know that this is a vector of W. That means cardinality have only one vector. Sorry, basis contain only one vector. So if you write in the set, so this is going to be no need to check it. You directly say this is a basis. You can directly say this is a basis because no need to check. Why? You know that the basis contain only one vector. So you put in the so you can directly say that this is going to be a basis. No need to check it here. If you want to check, you can check, but I am saying directly you can say because of this number. This one tells.
So here it is simple. Put Z is equal to 1 or either 0.
Yeah.
0, 0,
Yeah.
0.
So actually, it is difficult that then you already said that y is equal to minus 5z. Give some value to z here and.
Yes.
Okay. Directly from here you can tell. So that's the process. Use it. It will help you to.
So, sir, will it span to all the vectors of this subspace?
Yeah, actually it will span. No.
Okay.
So
okay.
you want to check it. You want to check it. You can check. Why I'm saying I'm not checking here because of this number 1.
Right. If we take z is equal to 2, then everything will be multiplied by 2, right?
Correct. That's the thing. Oh, means z is equal to 2. Okay, you can check that. Z is equal to 2.
If z is
Then
equal
y
to
is equal
2,
to
minus 10.
minus 10 and x is equal to minus 20.
Minus 20.
Minus
right?
20.
So yeah, actually now, yeah, any number, this can be generated. You can check that this is the multiple of this is now this minus 20, minus 10.
We cannot take any arbitrary vector like 2, 3, 5 because that is not part of this subspace. So we will not check for 2, 3, 5, right?
Yes, correct.
We will only check for those vectors who are satisfying these equations.
This equation. Because those vectors will come in only in W, and W, if those vectors are coming in W, it will be generated by this.
These vectors. Okay.
So this is the thing here. That's the I want to tell you the basis. I am not missing anything now.
Sir, or we can say the number of vectors depend on the number of independent variable.
So actually yes. Actually, if your subspace is given like this in the equation form, so if it is given in the equation form, so number of independent variable so this forms a system of linear equation, right? In this system of equation, how many independent variable have, that gives the dimension of that vector space. That's
or the number of vector in the basis.
No, number of vector in the basis. Yes. Correct.
Okay.
Okay, so I hope now need to stop the session. Is that if you have, you can ask.
So here confusion. Sir, previously you wrote y is equal to z plus 2. It is not satisfying because it is not passing from the origin. But through we can find basis.
No. So how the basis word only associate with the subspace or vector space, not for any general. If that set is not a vector space or subspace, so there is no mean to get the dimension. For that, that's why the affine word came, right? That's why the affine subspace came. If it is not passing through origin, so still we need to deal with, right? See, if there are planes which are passing through origin, we are dealing with in this case. But if there are planes which are not passing through origin, but still we have to deal. We are doing mathematics. We have to deal. So how we will deal? That's the word term affine. Affine is more general form of this subspace. Affines can deal with any because affine subspace not a subspace. It is a set, but this affines corresponds a subspace. This affines corresponds a subspace which pass through origin.
So clear, fine, sir.
Sir, can we consider it like a line passing through the origin, then we shift that by some constant?
That is the affine. So affine, actually, so affine is the plane, any plane, but still we want to study. So how we will study this? So we study only the vector subspace. If you are doing something, so or you are fighting with a very big guy, so what you will try to do, you will bring to him in your home, and then you will fight. So this is the big thing. Okay, what you will do, you will try to bring to home. So how you are bringing? You are bringing to it to your zone. You are bringing to its subspace. That means you are trying to find a corresponding subspace. Now bring it in your zone, and now deal with the whatever you want. You want to beat him, you want to do anything. do with that.
अपने बोलने में बढ़ाना पड़ेगा ये कह रहे हैं सर आप.
Oh, okay. Oh, sorry. So that's the thing I mean to say. Fine is if it is a very big guy, if it is an elephant, if it is lion, bring it to home and then beat him.
Now
Sorry,
it is not an elephant.
Sorry, last question, sir.
Yeah.
Hello, sir.
Yeah, I'm audible, right? No.
Yeah, sir. Sir, can we write vector subspace as 2y minus 5z z?
Okay, just 1 minute. 2y minus
5z. 2y comma minus 5z comma z.
2y minus 5
Z.
5z, okay,
comma z.
Comma z. So yeah, this is yeah.
And suppose we put y is equal to 0 and z is equal to 1.
Y is equal to 0 and z equal to 1. Okay. This one.
So we get 0. Yeah. So
This
we
one.
get 0 minus 5 1. Yeah.
So is this going to be a subspace?
No.
0 minus 5 1. No. Because it is not satisfying second equation. So
Second means 0 0. Because it's not 0 because z is 1 here.
Yes.
It is not going to be. If you erase this one and only collect this, so this is going to be a subspace.
No, sir, I am talking about previous question which you are doing where dimension is equal to 1.
Okay.
Yeah.
Here.
Yes.
So yeah, you can write this set. Yeah, actually you can write this set. Here you can erase and whatever you want to write, as you are saying, this is minus 5 set and this is minus 10 set. Yeah, so this is the another representation of W.
Yeah.
Yes.
So here, sir, first we put y is equal to 0 and z is equal to 1. Then we put y is equal to 1, z is equal to 0. So here we get two bases, I think. So dimension is 2, sir.
No. So you are confusing here. How you are x is equal to 2y and y is equal to minus 5 that you are getting. So here how it is happening? It is not happening now. Y is equal to, how you will substitute y is equal to 0, z is equal to 1. If you substitute here, what you will get? Substitute here. You will get like it is not happening also. Only see, y can be written as in z form. And this x can be written in y form. So that means whole x can be written in z form, y can be written in z form. Only need to give the value to z, right? No need to give. It is not happening to give the value, independent value. Y is dependent on z. X is dependent on z.
Okay. Y is depend on z and x is also depend on z.
On z. You can write it as a 10z minus 10z.
Okay. Now it's.
I have a question. Let's say we have my equation representing a plane x plus 3y plus 2z is equal to 0.
Previous one.
Yeah, any equation, just one equation for a plane.
Okay. What is that?
Okay.
Let's
take anything. X plus 3y plus 2z is equal to 0 or anything. It's okay.
Anything. Okay.
Okay. Now, how do I actually put the dependent and independent variables in this one? Because I can move y and z to the other side and call them independent. I can move x and y also, or I can move only one of them. Yeah. Which way do I
actually? So see, you can tell here the cases. You can say that y is equal to send this side and say y dependent on x and z. You can send x and y that side, and you can say z is dependent on x and y. But the case is here you are not solving a system of linear equation. So only you can say it have two independent variables. That's all you can say. Nothing more. But only you can say two independent variable. It can be any variable can be depend on any two. Only this you can do. You can tell. That's all.
Okay. Okay.
If you are dealing with the system of linear equation, then there you used to go with the RR, reduced row echelon form, whatever you got in small form, reduced row echelon form. From there, you used to say that okay, Z is going to be dependent or Y is going to be independent. So still in that, from not only that system of linear equation, in the matrix it is given that in the matrix is given in reduced row echelon form. From there you will decide that it is going to be independent or dependent. Not for the this system of linear equation itself. In the matrix is given, from there you will tell. Or system of linear equation is there right in the matrix form, and then change it in reduced row echelon form. Then from there.
Okay. Okay. Thank you. Thank you. And I have one question which is not on the current topic. Maybe towards the end, if you can help me, it'll be really great.
So we are actually approaching to end. So actually, I'm thinking to close the session. Yeah, almost done the what.
Can you just help me with this question on graded assignment 11?
11.
11.
Is over or not? I don't know.
It's done. It's done. And I did not get that question right. That's the reason I'm asking.
Due to personal constraints, I used to attend very less these live sessions, and usually I used to watching YouTube. I have one doubt in partial derivatives. Could you spare 5 minutes for me also, please?
Yeah, sure. So yeah, it's okay. We
Question 9, please. Question 9.
Question 9. Okay.
Yeah, this one I made a calculation and found exactly the opposite of what were the answers.
Oh, so it is
how to solve this is what I'm not really clear about.
Okay, as according to the option we need to evaluate. So it is for the checking for differentiability at 0, 0, and
continuity also at 0,
continuity
0.
of each. Okay. Okay, so let me do that this is okay. We have x minus y whole square
sine 1 by x minus y.
1 x minus y. This
when sine is when x is not equal to y, else it is 0.
And 0 if x is equal to y.
Yeah.
Okay. So this is our function. So I want to check it the options. According to the option, we need to go. We need to check if its continuity at 0, 0. So let's find the limit of first. How you will deal with it? You will find the limit of at 0, 0.
Okay.
Right? Limit at 0, 0. So means find the limit of it is if it is exist or not. So let's do that limit x y tending to 0, 0, 0. Okay. Our function is here as. So if xy is going to be 0, 0, so see that
it's not right.
It's
what is happening here. When x is equal to y, you have value
0.
So and okay. For the x and y not equal to 0, sorry, x and not equal to y, your function is this one. Oh, I was misunderstood. So it means to find limit x and y goes to 0, 0. This function.
Yeah.
So need to evaluate the limit of it. So how we will evaluate here limit?
इसको सर अगर हम ना sin 1 upon xy divided by 1 upon xy के फॉर्म में लिखे हैं और x minus y करके x minus y into sin 1 upon x minus y divided by 1 upon x minus y. So this would be the form of sin 0 by 0, that will be 1, and then it will become x minus y. Then if xy goes to 0, 0, x and y will be equal to 0.
Sin 0 by 0, y would be 1.
That is sin x by x form, right?
Actually, that is one case. And actually, this is happening. Actually, what is happening here? Okay, but it is need to be a formal way. You need to assume y is equal to x minus y is equal to z here. So your function is actually will change in the one single variable, which is z square sine 1 by z form. The condition is what? if x and y goes to 0, is that z is should also goes to 0. It is happening. So actually it is happening. No. If z is goes to okay. If x and y goes to separately 0, 0, is z is going to be 0 as you are changing here. So yeah, happening. So it will work. It will if you want to evaluate this limit, it will work. So you can deal with that. But that is the different thing. Like it is called a change of variable, but we didn't study this. So we will not prefer. We will go with the only what we have, and we have only to find a limit is sandwich theorem. So sandwich can deal here. Sandwich can easily deal here. Sine 1 upon x minus y. See this function, the sign is always a bound. It can vary from 1. So it is always 2. It will be like this.
-1 to 1.
Right?
Yeah.
-1 time this one, this function, and 1 time this one.
Right.
Our function is bound to on this two functions.
Yes.
Now sandwich tells evaluate the limit of separate these two. If these two goes to the same limit, then this one also will go to the same limit. So actually it is happening. If x and y goes to 0, this one is goes to 0, and this one also goes to 0. So sandwich tells that yeah, okay, this one is going to be 0. So actually limit is can be evaluated using the sandwich, and this is going to be 0 limit. And if limit is 0 and value at that point 0, 0 is 0. So your function is now going to be continuous.
Okay.
Now next is we evaluate the partial derivative.
Yeah.
So the same process, partial derivative with respect to x, I will evaluate that. So the partial derivative is that the options are is that partial derivative are going to be 0, 0 at same or not. So what is the definition, limit definition? Because you are doing with the
f of x plus h comma 0, x plus h comma y minus f of x y divided by h.
So it is going to be 0 plus h, 0 minus
0 plus
0, 0. So it is going to be h0, and this is going to be
that is anyway
0
going to be
upon h.
Yeah.
Now what is the value then here? The of h0. Our function is
h square sine 1 by h.
H square sine 1 by h. H square sine 1 by h upon h. So limit you can easily evaluate here, right? Limit h tending
h sine 1 by h is what it will
1 by h. What is going to be 0? No, I just quickly did it.
No, it can be 0. No, h sine 1 by h. Why would that be 0?
Again, the same thing, same process. It is it can be limit.
Okay,
H can be cancelled.
Okay.
Same thing. It is happening, no?
Okay,
Because
same sandwich.
Same thing is happening. You will get h times sine 1 by h, and you can again sandwich theorem you can use until that limit is going to be. Similarly, you can evaluate for partial derivative with respect to y. It will still give the same.
Okay.
Now need to check for. See, now tell me the definition for differentiability. What is the sufficient condition for differentiability?
1 second, please. We did it for x. Now, when I go to differentiation on y, it will be 0, comma h. That will be over h, which is okay, sine minus 1 by.
Still, it will work. It will be minus means h square.
Yeah.
Sine minus 1 by h. It will work, right? You can bound it and it will deal with the sign.
No, if it is going to come to 0, then okay, it's not equal. But both are equal. Okay, that is
it is happening 0.
Okay.
Now tell me the differentiability definition.
Differentiability.
Definition means is what is the sufficient condition for differentiability. Need to go with the partial derivative should be continuous. If the partial derivatives are continuous, then our function is going to be differentiable at 0, 0.
Yeah.
So you can evaluate that partial derivative. First, find the partial derivative in the general case.
Yeah.
So our function is x minus y whole square sine 1 by xy, my x minus y. So do that for the partial derivative separately. So this is, you can think as assuming to be the y fix and evaluate the first derivative with respect to x. So it is going to be 2x minus y. That's a
yeah, 2x minus y plus and
sine
sine
x minus y plus now x minus y whole square. It is
but
going to be
inside
if you do inside, it will give to 1. Inside will give 1.
Oh, yeah.
Right.
Divided by x square minus y square, isn't it?
Divided by
x minus y whole square.
X minus y. No. Only we are
second term.
Cos 1 by x. Cos 1 by x.
Second term will be divided, no, sir?
So it is not in this form. It is multiplication we are doing. We are
It is
differentiating the
form.
multiplication form, not in the division form.
No, sine 1 by x if I actually differentiate.
So here is I just differentiated this one. Still, it will be the same. Now
Correct.
it will be the same. I am differentiating this one.
Correct. Sine 1 by x minus y, if I differentiate, it comes to cos 1 by x minus
Cos 1 by x.
But 1 by x.
Now 1 upon need to be do that. It is going to be minus 1 upon x minus
1 by x
y
minus y whole 1 by x minus y whole square.
1 by
X minus y whole square.
no, so minus will come. So minus 1 upon x minus y whole square will come.
Why would it be minus? I'm differentiating after that x minus y.
You are differentiating only this one, right? So it
Yes.
is going to be cos 1 x minus y.
Okay.
Right?
Okay. Sorry. Yeah, got it. You're right.
So now you need to check that. Now find the limit of this at 0, 0, and value already evaluated, which is 0 here. So is limit exist at 0, 0?
Yeah.
It is going to be exist. No?
Existing because it's again sandwich. Okay.
No, I
so
think I'm missing something. It is going to be exist or not.
It is actually the answer is differentiable at 0. That's the reason why.
It is going to be exist, and I think I'm missing something. X minus y whole square cos 1 by x minus y. Okay, it is going to be because it is cancelling here.
Yeah, x minus y whole square will cancel on the numerator.
It is going to be cos 1 by x minus y. In that case, limit is not exist. No.
But cos also.
So answer will be only 1 upon cos x minus y. The next term will come. So in this case, limit will not exist at 0, 0 because you are getting 1 upon cos 0.
No, 1 upon cos. Cos 1 by x minus y. That's still
cos 1 by cos 1. Still, it will not be. Then the limit will not exist. This is 1 upon 0 kind of your finding. So it will do like this. 1 plus 1 minus 1 infinity you are getting.
But cos also tends to stretch from -1 to +1, right? Why would that actually?
So that's why I'm saying limit is not exist. So I think I'm missing something. That's why. Just 2 sine 1 upon something plus x minus y whole square. Okay, cos.
Does limit exist for the function? Can't we say partial derivatives are continuous?
Only we are checking partial derivative is going to be continuous or not. So we did partial derivative here. Now I am checking.
No, the function itself, we got the limit, right? Limit of the function is 0. We got. So from there,
differentiability is the next one, isn't it?
Differentiability is.
I should have the slope of the curve always. That is what I'm looking for. If it goes vertical, then it's no longer differentiable, right? It goes parallel to y-axis.
Okay, let's see that what is in solution.
Solution is it's differentiable.
So, but how he showed that? My condition is
that one is not uploaded. That's the reason why I'm struggling. Why I'm troubling you.
Okay. Let's see that how it's the solution have. Oh, solution is not uploaded.
Yeah, it's not uploaded.
It will be uploaded. The OPT. Okay, no issue.
We can try the first principle, na? F of a plus h minus.
Actually,
f of
there are two ways. Like I am doing like this, but we can go with the exact definition also. But I don't want because I tired. I become tired. That is a long process to telling me. Maybe I will quickly do that, but you people will not get that. That's why. See, there are two ways. Either you will check for the continuity of it. Either you just go the limit definition of the differentiability. Let me show you that. And that limit definition is dealing with that is not very easy. I need to go with this definition.
It's very difficult.
Not
Showing the limit exists is very difficult.
Not difficult. It will take time. I can tell
Practice.
Here. It will take time. So that, and already it's the session is 3 hours and more than 3 hours, 3:30 hours.
Can you explain me that for a few minutes? Is it possible?
That's why
I watched your previous end term session. That was you only. You mentioned that point in that session. That's what I'm asking you only now.
Here for this one.
No, not this one. This
okay,
9.4 question number 4. Last question.
Okay. I will discuss that. I will discuss this. Okay. Okay. Let's. Actually, I want to go with the solution that will be more better. Otherwise, if I will go with this one, it will take time. And
yeah, it's lengthy.
Otherwise, maybe I am missing something here.
For the next
I want to check continuity. Continuity is very easy. If you want to check the differentiability, continuity makes very easy. Sometime, yeah, actually it should be. I'm missing. Maybe I'm doing calculation mistake here. Okay, let me do that. I have x minus y whole square sine 1 upon x minus y only, right? This one. Okay, so partial derivative with respect, it will be 2x minus y sine 1 upon x minus y plus now x minus y whole square cos 1 upon x minus y. Now need to deal with inside minus 1 upon
x minus y whole square
minus y
whole square.
Whole square.
So numerator and denominator.
This is going to be cancelled out here.
Yeah.
So 2x minus y sine minus y
minus it's minus cos.
Minus cos 1 upon x minus y. And at 0, 0, if you will evaluate the limit, it will not, this side will exist, but this side will not exist here.
Raviji, let's leave this one. Can I ask my doubt?
Okay,
it's
just
too
one.
late also.
Okay, just 1 minute. Let me check it.
Let's discuss in the next session. Is it okay, Raviji?
It's okay as long as I get the solution sometime. I'm perfectly
No,
fine.
I'm just telling you, just 1 minute.
Mine will take just few minutes only. It's not lengthy.
Okay.
Can you please open 9.4 last 9.4 AQ?
Okay, just 1 minute.
I'm so sorry, Shubham.
No, it's my duty to do that. Just 1 minute.
Actually, you mentioned this in that previous end-term revision session. This based on degrees of freedom for these rational expressions, but I'm not able to understand. 9.4 last one.
Okay, I will post it in the Discord then. Maybe better. Okay, Raviji. Okay,
All
I
right,
will
thank
post
you.
it in the Discord.
Thank you.
In the Discord.
Thank you.
So which
Thank you.
activity? You said let's remain to your which activity?
9.4 last question.
9.4.
Rational expression. Actually, your screen is not visible.
Question. I will say. I stop the sharing. Which question number?
10.
10. Okay. 10. This one. Checking for the this one. So what is
Yes.
doubt here?
Actually, I didn't understood what's going on here. K greater than 2n, k less than 2n, k equals to 2n. These three cases
Okay.
I want to know.
Okay. So we have function this one.
In general, not only related to this question, in general, you explain how it
So actually, this is x to the power k y upon x to the power n y to the power n. X to the power n plus y.
take the general case. No need of 2n. Take general case.
Actually, this is itself in general case.
Acha, this 2n. Okay.
Actually, this is 2n. So this
normally, we will take xy by x plus y, x square y by x plus y, like that. Many expressions we are going through, right, in examples.
So actually, see that the simple same thing is using the sandwich theorem. This is this.
Sir, can we do it like this? If k is greater than 2n, this means the power of numerator is more than power of denominator, right? So somewhere that will cancel, and we have some term of x in that numerator.
Actually, that's the thing. That's the exactly thing. Using without sandwich.
Explain me the application part only.
Okay. So without sandwich, okay. So assume to be x is greater than 2n. Okay. So that means k. K is greater than 2n means greater than 2 means surely it will be 2n plus 1 or maybe greater than that. Okay.
Yes.
Okay. So let's for the simplicity assume for 2x k is actually 2n plus 1. So it is going to be 2n plus 1. Assuming to be k is equal to 2n for simplicity. You can make it in general form also. This is now x to the power n plus y to the power n. Yes. Now this is for the k here. Okay, so next is you can still it
if
will
we
be
take sir x to power because x to power 2n will get cancelled because x and y both not will be 0 together, right? If they are 0 separately, then no issue because then at least one term of the denominator will be non-zero.
So still I have to go with the sandwich. Still sandwich will work. It will not work. So sandwich will tell you. So see what is happening here. You can see x assume to be Assume to be x as a 2n plus 1. So x to the power 2n plus 1 or 2n plus 1 or
minus 1
or what I mean to say x to the power 2n plus 1. This case always will be true, right? Why? The reason is this is a square here. This is going to be positive. This is going to be positive. Okay, both are positive. So this number is always greater than this one. This
maybe
one.
Equals to also, right? No?
Maybe equal to also. Yes. And this number is for the cases. Cases are here. 2n minus k is equal to cases also made. Okay. So this number is going to be not greater than 0 because x is less than 0, then okay. This is going to be always true, and this is greater than 0. Just 1 minute. Let me go with the option. The limit is exactly equal to greater than it is always exist. Okay. Sorry, yeah. Whatever here I will write, I need it will not work here, because this is
It's
odd
okay.
number.
You please tell me what happens when it's greater than 2n, less than 2n, and equals to 2n. That's it. Application is enough for me.
So actually, what is happening? The if you are interpreting it, so actually the same thing. If k is greater than 2n, so
you can put
in the
y is
simple,
equals to mx, na? Here y is equals to ms.
that is the more, that is y is equal to mx is a specific case. That is, you are approaching to go with a particular way, particular particular path. But we need to prove it a more general case. So if you assume k is equal to greater than 2n, so the simple way is saying it have degree greater than below 2n, right? If it is greater than 2n, so means numerator have degree greater than this one in denominator. So x is always going to be a some kind of, means you can write it as some greater than x means x time.
Yes.
Oh, maybe here it will work. Oh, this is going
always x will be there.
This is going to be, oh, I just missed it. I was missing this. This is going to be, and in that case now you can divide it. This number will work for this one x for the general case. For the smaller case, zero 0.1.
I have a question here generally with this configuration that you have done. Complete it, please, and I'll ask the question. So maybe I don't understand it enough. That's the reason.
I mind it. Okay, I will tell you actually. Maybe I tired, that's why I'm not getting this time.
It's okay, leave about this. Just you tell me what happens when k less than 2n.
Actually, what is happening? So the power of numerator is going to be greater than 2n, means this is going to be the greater than in denominator power. So many times what happen, if it is greater than in the numerator have greater power, so if you take the limit of it, it will work as a x time 2n plus, what is happening here? It will happen like, let's assume k is equal to 2n plus m. So it will be m into x power 2n into y. So this will tells you, or maybe not only this one, it will become here. This will be give us some real number, but will be multiply with approaching to this. Actually, this is one case. I am not here telling the sandwich theorem. What is happening? This will give always some. It will bound some number, but this multiplied will go to 0. And the reason is, if it is like this 5x and x goes to 0, then this will go to 0. So this will be approached to a fixed number, and this is multiplied with the approaching to 0. That's why whole thing will approach to 0 when k is greater than 2n. And if it is less than 1, then in denominator you will get always a 0, because this is, if it is less than 1, so see, this is the degree of numerator is lesser than degree of denominator. So you will find a type of some real number upon 0 kind of when you do the limit of it. So in that
so
case,
we can take k less than 2n. Here they mentioned k less than 2n minus 1. Can you take k less than 2n?
Like 2n minus m, if you are right like this. This will work. This will work. So again, same thing.
No, I will say x by x square plus y square.
Sorry.
X y by
x
into y. X y by x square plus y square.
Here you are saying in numerator.
Yeah.
What you are saying? X
2n minus 1.
2n minus 1. Oh, so you are saying this one upon x.
2n minus 1, yes.
So that's the thing. So again, it will give a number here, but it is in denominator approaching to be 0. So you are getting some kind of this form. So in that case, your limit is not going to exist. And if k is exactly equal to 2n, so again I said it is going to be a fixing a number, not a fixing. It is means you can check that if k is equal to 2n, what is happening? K is equal to 2n means x to the power 2n y upon x to the, in that case also the limit will exist because having degree more than in denominator. So what are the answer here? Actually, it will not only this one.
Actually, in today mock, one question is there, xy by x plus y.
X, y, y by x plus y, okay.
Xy by x plus y. For this, limit doesn't exist.
So, you can actually, actually the reason is,
x plus y.
if you approach to this function with the line, with the curve,
it's x plus y.
X is equal to y. Sorry, x plus y.
Denominator is x plus y.
X plus y, okay.
Numerator is x into y.
X into
yes.
Y. So if you approach this function with this line, your approach to this line means you approach to 0 with this line, y is equal to minus x. What will happen? Limit will exist? No, because you are getting minus x square upon 0 kind of. So when you are approaching to 0 with this line, according to this path, limit is not exist. Except from this line, if you approach to any path, it will give to 0. I mean, it will give a limit. But if you approach to 0 with this path, y is equal to minus x. What is happening here? Substitute here. This is minus x square upon.
So this 2n concept is not in general cases. We cannot take it as a thumb rule. We cannot take it. K less than 2n, k equals to 2n.
No. It will work. It will work for greater.
But here xy by x plus y, it doesn't work, right?
So for this case, it is not happening.
This is k equals to 2n.
So here what is happening? Your k is equal to 2n. Yes. So see that for this case, if k is equal to 2n, so limit is exists only for greater than, not for smaller, not for equal to also, only for greater than 2n. Right?
Okay. No, equals to 2n case is not given here.
But still you can check that. Yeah, actually, I will tell you. I will also post this solution this time. Okay, I will post this solution. But,
okay, fine.
Yeah, I will post the solution properly written.
One question.
My mind is.
You must be tired also. It's too late.
Yeah, it's. I'm running it from 4 hours continuously.
Yeah. Sorry.
Sorry to impose upon you, but just wanted this clarity on what you had written there. X power 2n plus y power 2n is greater than x power 2n plus 1.
Okay, I will. If I will post it a proper solution, then you will easily get that.
No. I'm not asking solution for that. I'm not asking solution for that. What I want to ask is, if y is less than 0, if y is less than 0 in decimals, not negative number but decimals, it tends to go lower as you try to get it into higher power.
That's why I stuck. That's why I stuck in making the inequality. That's why I was not unable to stack the unable to make the inequality. That's why I was thinking.
Okay.
That's why I was stuck there.
Okay. All right. Thank you.
Okay. Maybe.
Thank you. Good night.
Good night.
Thank you. Thank you.